There's a quiet idea that moves through the internet late at night. It whispers that something is not quite right, that reality feels thinner somehow, that strange memories, strange headlines, strange feelings might mean the fabric of existence itself has been disturbed. And very often, when people look for a cause, they land on one place: CERN. The name alone sounds mysterious. 4 short letters. Clean, sharp, almost secretive. If you've ever searched it, you probably saw images of a massive underground ring buried beneath the border of Switzerland and France, a machine that stretches for 27 kilometers, about the length of driving across a small city from one side to the other. If you tried to walk that distance, it would take you around 5 or 6 hours without stopping. And this entire ring sits deep underground, in tunnels wide enough for trucks to drive through. That already feels like science fiction. A giant circular machine hidden below the Earth, smashing tiny pieces of matter together at speeds close to the speed of light. It sounds like something from a movie where scientists accidentally open a doorway to another universe. So it's not surprising that some people wonder, what if they pushed too far? What if they broke something? What if reality itself cracked? When you hear phrases like particle accelerator or colliding protons at nearly the speed of light, it doesn't feel ordinary. It feels powerful, dangerous, almost cosmic. And the scale adds to that feeling. The main machine at CERN, called the Large Hadron Collider, is buried about 100 meters underground. That's about as deep as stacking 30 apartment floors on top of each other, and then going down that far beneath the surface. Down there, powerful magnets guide tiny particles around the ring over and over again, like race cars speeding along a circular track. Except these cars are smaller than anything you can see, even with a microscope. When people imagine this, they don't picture harmless science experiments. They picture rips in space, portals, black holes, other dimensions. It's interesting how the human mind works. The bigger and more hidden something is, the easier it becomes to imagine that it's doing something extraordinary, maybe even something secret. If someone builds a small machine in a garage, we don't worry about reality collapsing. But if a group of scientists from around the world builds a machine the size of a city loop, buried deep underground, using some of the strongest magnets ever created, it begins to feel mythic. And then there are the images. You might have seen the statue outside CERN, the statue of Shiva, the dancing figure from Hindu tradition. For some people, that statue alone sparks wild ideas. A god of destruction standing outside a particle collider. It feels symbolic, mysterious, almost cinematic. But symbolism has a way of stretching in the imagination. Add to that the language physicists use, words like energy levels, quantum fields, symmetry breaking, dark matter. These aren't everyday phrases. They sound like pieces of a hidden puzzle. So a question naturally forms. If this machine is smashing particles together with enormous energy, could it tear a hole in reality? And if it could, would we even know? It's a fair question, not a foolish one. When something feels powerful and unfamiliar, curiosity mixes with caution. But before we imagine reality splitting open like cracked glass, it helps to pause and gently look at what CERN actually is. CERN is not a secret military lab. It's a research center where thousands of scientists from many countries work together. Think of it less like a hidden bunker and more like a global science campus. Its goal is simple in concept, even if the details are complex. To understand what the universe is made of, if you break everything around you down, your chair, your phone, your hands, and keep breaking it into smaller pieces, you eventually reach particles so tiny that they are hard to even imagine. These are the building blocks of matter. CERN studies those building blocks. That's it. No spells, no rituals, no attempts to rip open the sky, just questions. What are we made of? How did the universe begin? Why does matter exist at all? But then another thought appears. If they are recreating conditions similar to the early universe, even on a tiny scale, doesn't that sound risky? After all, the early universe was unimaginably hot and dense. It was a place of extreme forces. If CERN is simulating even a small piece of that, isn't that dangerous? This is where scale becomes important. Yes, the collisions inside the Large Hadron Collider are powerful, but powerful in a very specific way. The energy is concentrated into particles so small that trillions of them could fit inside a grain of sand. It's like focusing a lot of energy into something smaller than a speck of dust you'd struggle to see floating in sunlight. It sounds dramatic, but it's controlled, measured, observed. Still, the feeling remains for some people. The world seems strange lately. Memories feel uncertain. Headlines feel surreal. Technology moves fast, so when something enormous and complex operates underground, out of sight, it becomes a symbol for change, for instability, for the idea that maybe something shifted behind the scenes. But here's a gentle thought. What if reality hasn't broken at all? What if it simply feels fragile because we are looking at it more closely than ever before? CERN doesn't claim to control reality, it studies it. It asks quiet questions about the smallest pieces of existence. And when we hear about these questions without context, they can sound like doorways to unknown worlds. But curiosity doesn't equal danger. In fact, curiosity is what brought us electricity, medicine, satellites, and the very devices we use to wonder about these things in the first place. So as we begin this journey, we can hold two ideas at once. Yes, CERN sounds mysterious. Yes, smashing particles at near light speed sounds dramatic. But mystery doesn't automatically mean threat. Sometimes it just means we're standing at the edge of understanding something very small, and very old, and very fundamental. And that can feel just as powerful as any story about tearing holes in reality. As the night continues, we can slowly explore what this machine truly does, what physics actually allows, and whether reality is really as fragile as it sometimes seems. For now, just let the idea settle. A giant ring beneath the Earth, humming quietly, not trying to break the universe, but trying to understand it. As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. If you imagine the Large Hadron Collider for the first time, your mind might picture something wild. Maybe a glowing tunnel filled with lightning, maybe swirling portals opening like doorways in the air. But the reality is much quieter. At its heart, the Large Hadron Collider, often called the LHC, is a very large circular track buried underground, stretching 27 kilometers, about as long as driving from one end of a busy city to the other. If you placed city buses end to end, you would need more than 300 of them to match that length. Inside this ring are long metal pipes. These pipes are not wide like highways, they are narrow, more like large plumbing tubes running for miles. Inside those tubes, tiny particles travel. What kind of particles? Mostly protons. A proton is one of the small building blocks inside every atom, and atoms make up everything you see. Your desk, your clothes, the air, even your own body. If you could zoom in far enough, deeper than any microscope can go, you would find these protons sitting inside atoms. The LHC takes protons and accelerates them. What does that mean? Think of it like pushing a swing. At first it moves slowly, but with each push, it goes faster and faster. The LHC uses powerful magnets to guide protons around the circular track, pushing them closer and closer to the speed of light. Now, the speed of light is incredibly fast, about 300,000 kilometers per second. That's fast enough to circle the Earth about 7 times in just 1 second. The protons inside the LHC move just a tiny fraction slower than that. That sounds intense, and it is impressive. But here's something important to understand. These protons are unbelievably small. You could fit trillions upon trillions of them inside something as small as a grain of sand. So even though they move very fast, they don't have the kind of power you might imagine when you think of speeding objects. After accelerating 2 beams of protons in opposite directions around the ring, scientists guide them to collide at specific points. Why collide them? Because when 2 protons smash together at very high speed, they break apart. And when they break apart, they reveal smaller pieces and release energy that scientists can measure. It's a bit like smashing 2 watches together to see what gears are inside. Except instead of metal gears, we're talking about tiny particles that existed just after the universe began. So when people hear collisions at near light speed, they sometimes imagine explosions. But these collisions happen at a scale so small that they are almost impossible to picture. The energy released is real, but it's concentrated into a space far smaller than anything we experience in daily life. You might wonder if they are recreating conditions similar to the early universe. Isn't that risky? It's true that the collisions briefly create temperatures hotter than the center of the sun, but here's the key. They do so in a space smaller than an atom, and for a time shorter than a blink, shorter than a trillionth of a second. It's like striking a match that burns for less time than it takes a single raindrop to fall 1 millimeter. It sounds dramatic, but it's controlled and extremely tiny. The detectors surrounding these collision points are enormous machines themselves. Some are as tall as a 5-story building. Imagine stacking 5 houses on top of each other. That's about the height of one detector. They weigh as much as thousands of cars combined, yet their purpose is simple: to observe and record what happens in those tiny collisions. They don't open doors. They don't create swirling vortexes. They measure data. So, where does the misunderstanding begin? Part of it comes from language. When scientists say they are recreating the early universe, they mean recreating similar energy conditions on a microscopic scale. But that phrase can easily sound like they are trying to rewind time itself. Another part comes from imagination. When you hear the most powerful machine ever built, your mind fills in the rest. But here's a gentle question. If smashing particles at high speed could tear reality apart, wouldn't nature have done it already? Every day, Earth is hit by cosmic rays, particles from space, that carry more energy than the collisions inside the LHC. These cosmic rays crash into our atmosphere naturally. They have been doing so for billions of years. Long before humans existed, long before cities or satellites. And reality is still here. That doesn't mean we stop asking questions. It simply means that the LHC operates within physical limits that the universe itself has already tested many times. So what does the LHC actually give us? It gave us the discovery of the Higgs boson in 2012. That discovery helped confirm why certain particles have mass. Without mass, matter wouldn't clump together. Stars wouldn't form. Planets wouldn't exist. You wouldn't be here listening. That's not tearing reality apart. That's understanding why reality holds together. But it's easy to see how the scale, the secrecy of underground tunnels, and the language of physics create a sense of mystery. A 27-kilometer ring underground. Magnets cooled to temperatures colder than outer space, colder than the dark space between stars. In fact, parts of the LHC are cooled to about minus 271 degrees Celsius, which is just a tiny fraction above absolute zero. That's colder than Pluto's surface, colder than most of the universe. That detail alone sounds otherworldly, but cooling magnets to extreme cold simply allows electricity to flow with almost no resistance. It's engineering, not enchantment. So as we sit with this image, a vast circular machine humming quietly underground. We can gently separate imagination from function. The LHC accelerates particles, it collides them, it records what happens. It helps us understand the smallest pieces of the universe. It does not aim to break space. It does not aim to open portals. It studies, and sometimes, when we look closely at how something truly works, the mystery doesn't disappear. It changes shape. Instead of asking whether it could tear a hole in reality, a new question begins to form. If the LHC is only studying what already exists, then what exactly is reality made of? And is it stronger than we think? That's where the story becomes even more interesting. Somewhere along the way, the idea began to grow, not just that CERN was studying tiny particles, but that it might open something. A doorway, a portal, a tear in the fabric of space. It's a powerful image, isn't it? A machine so strong it rips reality like paper. A hidden gate between worlds. The kind of idea you'd expect in a late-night science fiction film. But where did this idea actually come from? Part of it traces back to the way physicists talk about extra dimensions. You may have heard someone say that there could be more than the 3 dimensions we move through every day. Length, width, and height. And when people hear extra dimensions, it's easy to picture hidden rooms just beyond our walls. Invisible corridors we might accidentally open. But that's not quite what scientists mean. In some versions of string theory, one of the mathematical attempts to describe the deepest laws of nature, the equations only work if the universe has more dimensions than we can see, sometimes 10, sometimes 11. That sounds wild. So the natural question appears, if these dimensions are real, where are they? Are they floating next to us right now? Are they stacked like layers of paper? Could the LHC punch through into one? The answer, in simple terms, is no. At least not in the way people imagine. When physicists talk about extra dimensions in string theory, they usually mean dimensions that are extremely small, not hidden like a secret room behind a wall, more like something curled up so tightly that it's impossible to notice. Here's a way to picture it. Imagine a long garden hose lying across your yard. From far away, it looks like a simple line. One dimension, length. But if you walk closer, you see that the hose also has a circular shape around it. Ants crawling on the hose can move forward and backward along its length, but they can also move around its tiny circular surface. To you, from far away, that circular dimension was invisible. String theory suggests that extra dimensions might be curled up in a similar way, but at a scale far smaller than atoms. So small that even our most powerful machines can't directly see them. They're not open hallways waiting to be entered. They're tightly folded into the fabric of space itself. So how did curled up microscopic dimensions turn into CERN opening portals? Part of it is the way news headlines simplify things. A scientist might say, "We are testing whether extra dimensions exist." That gets translated into scientists searching for hidden dimensions. And then, in online forums, that becomes, they're trying to access other dimensions. The language slowly stretches, and the imagination fills in the gaps. It's also true that some theories suggest that if extra dimensions exist, high-energy particle collisions might reveal tiny hints of them, not open doorways, just subtle changes in how particles behave, slight differences in energy patterns, small clues in data. But to someone unfamiliar with the math, that can sound like knocking on the door of another universe. So let's gently ask the question many people wonder. Could the LHC create a portal? To answer that, we need to think about scale again. The collisions inside the LHC happen at incredibly small distances, far smaller than anything we can see, even smaller than atoms. If extra dimensions exist, at that tiny scale, the most the LHC could do is reveal a slight fingerprint in the data, a tiny shift in how particles scatter. It would not create a glowing doorway in the air. It would not rip open space like fabric tearing. It would not swallow cities or distort the sky. Physics doesn't work that way. Another reason the portal story gained attention is because of the phrase high energy. In everyday life, high energy means something explosive or dramatic, but in particle physics, high energy refers to energy concentrated into very tiny particles. It's like comparing a lightning strike to a spark from static electricity. Both involve energy, but one lights up the sky and the other barely stings your finger. The LHC collisions, while impressive in their context, are microscopic events. And here's something calming to remember. Nature performs even higher energy collisions all the time. Cosmic rays from deep space crash into Earth's atmosphere every single day. Some carry far more energy than anything the LHC can produce. They've been hitting Earth for billions of years, long before humans ever built accelerators. If high-energy particle collisions could open portals, the universe would have done it already. So why does the portal idea feel so convincing to some people? Because it's dramatic. Because it turns abstract math into a story. Because the thought of hidden dimensions brushing against our own sparks, wonder and fear at the same time. It's much easier to imagine a door swinging open than to imagine a subtle shift in a particle's decay pattern. But the real story of extra dimensions, if they exist, is quieter, more subtle, more mathematical, and perhaps even more mysterious. Instead of asking whether CERN can open a portal, maybe the deeper question is this: what would it even mean to open a dimension? Dimensions in physics are not places you travel to. They're ways of describing how space and time behave. They're part of the structure of reality, not rooms attached to it. So, when we hear someone say they're trying to open another dimension, it helps to pause and gently untangle the idea. The LHC is not trying to tear into something hidden. It's trying to measure, to observe, to understand. And sometimes the truth, though less dramatic, is far more fascinating. Because if extra dimensions do exist, they are not waiting to swallow us. They are woven quietly into the universe itself. And that kind of mystery doesn't need a portal to be extraordinary. Now here is where the story becomes a little more intense. At one point, before the Large Hadron Collider even turned on, some physicists openly discussed a possibility. A very small possibility. They said that in theory, tiny black holes might form during high-energy particle collisions. That sentence alone was enough to spark fear. Black holes. The word feels heavy, final, cosmic. When most people picture a black hole, they imagine something enormous, a dark sphere in space, swallowing stars. And those do exist. Some black holes are as heavy as millions or even billions of suns combined. Imagine stacking suns the way you stack oranges in a grocery store. Except, you'd need millions of them just to match one of those giants. But the black holes discussed in relation to the LHC were nothing like that. They were theoretical microscopic black holes. So what does that mean? First, let's gently ask, what is a black hole? In simple terms, a black hole forms when a large amount of mass gets squeezed into a very small space. Gravity becomes so strong that not even light can escape. That's why they appear black. But gravity depends on mass, and this is where scale becomes everything. The sun has enormous mass. It weighs about 2 billion tons. That's a number so large it's hard to picture. It's like trying to count every grain of sand on every beach on Earth, and then multiplying that many times over. When stars much heavier than the sun collapse, they can form black holes. The LHC, however, does not compress stars. It collides protons. Protons are unbelievably tiny and light. You would need more protons than you could count in a lifetime just to equal the weight of a speck of dust. So how could anyone even suggest black holes might form? The idea came from certain theoretical models, where gravity might behave differently at extremely small scales. If extra dimensions exist, some equations suggest that gravity could become stronger in those tiny regions. And under very specific conditions, microscopic black holes might briefly form. But here is the key word: briefly. Even if such a tiny black hole formed, something smaller than a proton, it would not grow. It would not swallow the Earth. It would not drift through space like a monster. Why? Because of something called Hawking radiation. This idea was proposed by Stephen Hawking, one of the most well-known physicists of the last century. Hawking suggested that black holes are not completely black. They slowly lose energy over time by emitting radiation. For large black holes, this process is incredibly slow. A black hole as massive as our Sun would take far longer than the current age of the universe to evaporate. Imagine waiting not just millions or billions of years, but trillions upon trillions of years. It's almost beyond imagination. But the smaller the black hole, the faster it evaporates. A microscopic black hole, if it formed, would evaporate almost instantly. Not in seconds, not even in milliseconds. More like in a tiny fraction of a second, so small it's hard to picture. Shorter than the time it takes light to travel the width of a human hair. It would appear and vanish before it could do anything. So let's gently ask the natural question. If microscopic black holes were possible, could one somehow grow instead of evaporate? For that to happen, it would need to pull in surrounding matter faster than it loses energy. But at that tiny size, gravity would be unbelievably weak, much weaker than the electromagnetic forces that hold atoms together. It wouldn't start swallowing the Earth. It wouldn't even swallow a grain of sand. It would fade away almost instantly. And here's another calming thought. Nature already performs experiments far more powerful than the LHC. Cosmic rays strike Earth's atmosphere every day with energies higher than those produced in the collider. These natural particle collisions have been happening for billions of years. Longer than mountains have existed, longer than life has existed. If high-energy collisions could create dangerous black holes, Earth would have experienced that long ago. But we're still here. The oceans are still here. The sky is still above us. So why did the black hole idea cause so much alarm? Because the word black hole carries emotional weight. It sounds like the end of everything. And when you combine that word with a giant underground machine, the imagination does the rest. But in physics, size changes everything. A black hole the mass of a star is terrifying in space. A black hole with the mass of a proton, if such a thing could even briefly exist, is nothing like that. It's like comparing a hurricane to a dust particle. The word storm applies to both in a broad sense, but their impact is not even close. Still, the discussion around microscopic black holes reminds us of something deeper. Physics is honest about possibilities. Scientists don't hide theoretical risks. They calculate them, they publish them. They invite other scientists to check their work. Before the LHC ever turned on, safety reviews were done. Physicists around the world examined the math. They compared collider energies to natural cosmic rays. They looked carefully at every scenario, and the conclusion was calm and clear. Even in the most extreme theoretical cases, there was no realistic path to danger. So when we hear whispers about black holes forming in laboratories, it helps to slow down and picture scale. Picture something smaller than an atom. Picture it vanishing almost instantly. Picture nature performing stronger experiments every day above our heads, and then ask gently, is the fear coming from physics or from the power of the words themselves? Sometimes the universe sounds more dangerous than it actually is, and sometimes the real story, the careful math, the quiet evaporation of tiny possibilities, is far less dramatic than the rumor. But it is also far more reassuring. There is another idea that often appears in late-night conversations about CERN. Not black holes this time, but wormholes. The word itself feels like a secret passage, a tunnel through space, a shortcut between distant points in the universe. If black holes sound like cosmic traps, wormholes sound like cosmic doorways. So what exactly is a wormhole? To understand that, we have to step back and look at how modern physics describes space and time. According to Einstein's theory of general relativity, space and time are not rigid and flat like a sheet of glass. They are flexible. They can bend and curve. A helpful way to picture this is to imagine a large rubber sheet stretched tight. If you place a heavy bowling ball in the center, the sheet dips. Smaller marbles placed nearby roll toward the dip, not because something is pulling them with a rope, but because the surface itself is curved. That curved sheet is a simple way to imagine gravity. Now, a wormhole is a mathematical solution to Einstein's equations. In simple words, the math allows for a tunnel that connects two distant points in space-time. Imagine taking that rubber sheet and folding it so two distant spots touch. Then imagine poking a hole straight through both layers at once. Instead of traveling across the sheet from one end to the other, which might take a very long time, you could go straight through the shortcut. That's the basic picture of a wormhole. It sounds incredible. And naturally, the question appears, could something like the Large Hadron Collider create one? Before answering that, it helps to understand something important. Wormholes, as described in general relativity, are mathematical possibilities. They are solutions on paper. The equations allow them. But allowing something in math is not the same as creating it in reality. There are many mathematical solutions in physics that describe things we have never observed. And even if wormholes could exist physically, keeping one open would require something very unusual. It would require what scientists call exotic matter. What is exotic matter? It's matter with negative energy density, something that behaves in the opposite way of normal matter. Instead of pulling space inward like gravity does, it would push outward. So far, we have never found large amounts of such matter. We see tiny quantum effects that hint at strange behaviors, but nothing remotely close to what would be needed to hold a wormhole open. And the amount required would not be small to keep even a tiny wormhole stable, something just large enough for a single particle. You would likely need energy comparable to that found in stars, not the energy of a laboratory machine, not even the energy of all the power plants in the world combined. The LHC, impressive as it is, does not come close to that scale. Let's return to scale for a moment. The energy in a single proton collision at the LHC is tiny in everyday terms. It's concentrated into a very small space, but the total energy involved is about the same as the energy of a flying mosquito. Yes, it's moving at nearly the speed of light, but its mass is so small that the overall energy is modest. Now compare that to what would be needed to bend space-time dramatically enough to form a wormhole. You would need something closer to the energy of massive stars collapsing, events so powerful they shape galaxies. It's like comparing a matchstick to a volcano. So why do people imagine CERN opening space-time tunnels? Part of it comes from the language of high energy and collisions. Part of it comes from science fiction, where particle accelerators often serve as plot devices for interdimensional travel. But physics, as it currently stands, does not support the idea that smashing protons together could rip space-time open like fabric. Space-time is not a thin curtain that tears easily. It is more like a deeply woven structure, held together by fundamental forces that have shaped the universe for billions of years. And here's something else to gently consider. If wormholes could form easily from high-energy collisions, the universe would already be full of them. As we mentioned before, cosmic rays strike Earth with even higher energies than the LHC produces. And not just Earth. Every planet, every star, every cloud of gas in space. These collisions have been happening constantly for billions of years. If high-energy particle impacts created stable wormholes, space would look very different. But we see no evidence of tunnels opening in the sky, no sudden shortcuts appearing between stars. So let's pause and ask, are wormholes completely impossible? Physics does not say they are impossible. It says they are extremely speculative and would require conditions far beyond anything we can create. That's an important difference. Not impossible, but not something a 27-kilometer ring underground can casually produce. Sometimes, when people hear that wormholes are allowed by the equations, they imagine scientists are close to building one. But the gap between mathematical possibility and physical engineering can be enormous. It's like saying the equations of motion allow you to throw a ball into orbit. Which is true, but you would need enormous speed and energy to actually do it, far beyond what your arm can provide. In the same way, the equations allow wormholes, but the energy required would be staggering. So, when the idea appears online that CERN might open a space-time tunnel, it helps to gently return to what the machine actually does. It accelerates protons, it collides them, it measures the results, it does not fold space like paper, it does not punch holes through the universe. Wormholes remain a fascinating idea. They stretch the imagination. They remind us that the universe is stranger than everyday experience. But they are not waiting beneath Switzerland, and they are not humming quietly in a circular tunnel. The mystery of space-time remains profound, but it is not fragile in the way rumors suggest. It is vast, it is stable, and it has endured far greater forces than anything we can produce on Earth. There is another word that often appears in conversations about CERN: dark matter. It sounds mysterious, almost magical, something invisible that fills the universe, something we cannot see, cannot touch, cannot fully explain. And whenever we hear about scientists searching for it, a quiet question appears. If they are trying to study something we cannot see, could they accidentally unleash something we do not understand? Let's slow down and gently look at what dark matter actually is. First, here's the surprising part. Most of the matter in the universe is not the kind we are made of. The atoms in your body, the carbon, oxygen, hydrogen, make up only a small portion of the universe's total matter. In fact, everything we can see with telescopes, stars, planets, galaxies, accounts for only about 5% of the universe's total energy and matter combined. The rest, about 27%, appears to be dark matter, and about 68% is something even stranger called dark energy. That means the visible universe, the glowing stars and swirling galaxies, is like the tip of an iceberg. Imagine looking at a massive iceberg floating in the ocean, but only seeing the small white peak above water. The hidden bulk below the surface is much larger. So how do we know dark matter exists if we can't see it? Because of gravity. When astronomers observe galaxies rotating, they notice something strange. The outer edges of galaxies spin much faster than they should, based on the visible matter alone. It's as if there is extra mass holding them together. Picture a merry-go-round spinning. If it spins too fast, the outer riders should fly off, but galaxies don't fly apart. Something invisible seems to be adding extra gravity, keeping them intact. That invisible mass is what we call dark matter. But here's something important. Dark matter is not magical. It does not glow. It does not open portals. It does not behave like smoke or shadow. It simply does not interact with light the way normal matter does. That means we can't see it directly, but we can measure its gravitational effects. So where does CERN come in? Some experiments connected to CERN try to detect particles that could make up dark matter. The idea is not to create dark matter from nothing. The idea is to see if certain particle collisions produce signals that match what we expect dark matter particles might look like. In other words, they are looking for tiny hints in the data. Now here's a calm and important question. If dark matter makes up so much of the universe, Isn't it dangerous? If it's everywhere, why aren't we affected by it? The answer is surprisingly simple. Dark matter barely interacts with normal matter at all. Right now, as you sit or lie down listening to this, billions of dark matter particles may be passing through your body every second, through your walls, through the earth itself. And you don't feel a thing. It doesn't push you. It doesn't heat you. It doesn't disturb you. It interacts mainly through gravity, and even that interaction is very weak at small scales. So when scientists try to detect dark matter, they build extremely sensitive detectors. These detectors are often placed deep underground, shielded from noise and interference. They are trying to catch the faintest possible interaction. If dark matter were easy to control or dangerous to unleash, we would have seen effects long ago. It fills galaxies. It surrounds us constantly, and yet it remains quiet. Now, what about exotic matter? This is another phrase that sounds dramatic. Exotic matter refers to hypothetical forms of matter with unusual properties, like negative energy density. It's often mentioned in discussions about wormholes or warp drives. But here's the key. Exotic matter has not been observed in any stable, usable form. There are small quantum effects, tiny fluctuations at incredibly small scales, that hint at unusual energy behaviors. But these are not lumps of strange glowing material sitting in labs. They are subtle, mathematical features of quantum fields. So when people hear that CERN studies dark matter or exotic physics, they sometimes imagine scientists playing with unstable substances. But in reality, CERN is not storing barrels of mysterious cosmic material. It's studying particle collisions. It's measuring patterns. It's analyzing data. Let's return to scale once more. The detectors at CERN are large, some as tall as a 5-story building and weighing as much as thousands of cars stacked together. But what they are observing are events happening at distances far smaller than atoms. If dark matter particles are produced in a collision, they would not linger like a gas filling the tunnel. They would pass through almost everything without interacting, just as they already do naturally in the universe. So a gentle question forms. If dark matter is already everywhere, what exactly would CERN release? The universe is already full of it. CERN isn't opening a container. It's trying to understand what is already woven into the cosmos. And that leads to a deeper realization. The universe is far stranger than we once thought. Invisible matter shaping galaxies. Forces acting quietly across vast distances. Particles passing through us without a trace. But strange does not mean unstable. Mysterious does not mean dangerous. Dark matter is one of the greatest puzzles in science. But it is not a sleeping dragon beneath a laboratory floor. It is part of the structure of the universe itself. Calm, steady, and ancient. And as we continue, we may begin to see that reality does not need to be torn open to feel extraordinary. It already holds mysteries deeper than any portal story. And sometimes, understanding those mysteries brings comfort rather than fear. At some point, the conversation about CERN took a strange turn. It moved away from black holes and wormholes and into memory. People began saying that something felt different. Small details from the past didn't match what they remembered. Logos looked slightly altered. Movie lines felt off. Historical events seemed to shift in subtle ways, and this feeling gained a name: the Mandela effect. The name comes from a shared false memory that many people once had. The belief that Nelson Mandela died in prison in the 1980s, when in reality he was released and later became president of South Africa, passing away in 2013. When large groups of people remember something incorrectly in the same way, it feels unsettling. It feels like reality changed. And when the Large Hadron Collider restarted after upgrades, some people connected the two. They asked, what if the collider altered our timeline? What if a high-energy experiment nudged reality slightly sideways? What if we slipped into a neighboring universe that is almost identical, but not quite? It's a fascinating idea, but let's slow down gently and explore it. First, memory is not a perfect recording device. It feels like it should be. When we remember something clearly, it feels solid, stable, like a video saved in a file. But memory doesn't work like a video camera. It works more like storytelling. Each time we recall something, we rebuild it. We piece it together from fragments. And sometimes, small details shift. Psychologists have shown that memory can be influenced easily. If someone suggests a detail, even casually, it can blend into your memory. Over time, you may feel completely certain it was always there. Think of it like retelling a story from childhood. Each time you tell it, small pieces change, a detail becomes sharper, a word gets replaced. And after years, you're not remembering the original event, you're remembering the story you've told about it. Now imagine millions of people sharing the same culture, the same media, the same advertisements. If a brand logo is slightly misread, or a movie line is paraphrased in a popular way, many people may adopt the same version. It spreads quietly, and when someone later points out the difference, it feels shocking. Wait, that's not how I remember it. That moment creates a sense of instability, and here is where CERN becomes part of the story. The Large Hadron Collider restarted several times over the years after upgrades. Each time it made headlines, and around those times, people online would connect their strange memory experiences to the collider's activity. The thought goes like this: if the LHC is smashing particles at extreme energies, maybe it shifted us into a slightly different timeline. But let's gently ask a question. If reality had shifted, even slightly, would only small brand logos change? Would only movie quotes adjust by a word? Or would something far more dramatic happen? If the laws of physics were altered enough to move us between universes, even slightly different ones, the consequences would not be subtle. Atoms might behave differently. Stars might not shine the same way. The chemistry that allows life might not work. Reality is held together by incredibly precise physical constants. Tiny changes in those numbers, changes smaller than the width of a single hair compared to the Earth's diameter, could prevent stars from forming at all. So if we had slipped into a new universe, it would likely not feel almost identical. It would feel completely different, or we would not be here at all. Another calming thought. Cosmic rays strike Earth every day with more energy than the LHC produces. If high-energy particle collisions could shift timelines, the universe has been performing that experiment naturally for billions of years. And yet, history feels continuous. The Earth still orbits the Sun. The stars still rise and set. The laws of physics remain steady. That doesn't mean the Mandela effect isn't interesting. It absolutely is. It reveals something beautiful and strange about the human mind. We are pattern-seeking creatures. Our brains fill in gaps. We prefer familiar shapes and sounds. When a brand name sounds slightly off, our mind smooths it into something that feels right. For example, many people remember certain logos having details they never actually had, or they remember famous movie lines slightly differently from how they were spoken. Why? Because the altered version sounds smoother or fits the rhythm of language better. Our brains optimize memory for meaning, not accuracy. So when someone feels that reality has changed, it's not foolish, it's human. It's the natural discomfort that comes from discovering that memory is flexible. And when something as mysterious as CERN exists in the background, a massive underground machine dealing with invisible particles, it becomes an easy symbol to attach to that feeling. But the connection is emotional, not physical. The LHC studies subatomic particles. The Mandela effect studies human memory. One deals with quantum fields. The other deals with how our brains reconstruct stories. They operate in completely different realms. Still, the idea of timeline shifting is powerful. It speaks to a deeper curiosity. What if reality isn't as fixed as it seems? That question is worth exploring, but it doesn't require a machine to answer it. It begins inside the mind itself. And as we move forward, we'll see that the mysteries of physics are already strange enough, without needing to imagine that small changes in memory mean the universe has been torn and stitched back together. Sometimes the strangeness is closer to home, and sometimes understanding how we remember brings more clarity than fear. As the story of CERN spread across the internet, certain names began to appear again and again. One of them was Dr. Astrid Stuckelberger. Clips of interviews circulated online, short videos, quotes shared without full context. In these clips, she spoke about CERN, about experiments, about possibilities, and for many viewers, her words sounded like confirmation that something unusual was happening behind the scenes. When someone with an academic title speaks confidently, it carries weight, it feels official. It feels like insider knowledge, so it's important to slow down and ask a calm question. What exactly was said? And how does it compare to peer-reviewed scientific research? Dr. Stuckelberger has a background in public health and aging research. She has worked with international organizations, but she is not a particle physicist working at CERN. She is not part of the teams running the Collider experiments. That doesn't automatically dismiss her opinions, but it does matter when evaluating claims about highly technical physics research. In some interviews, she spoke about portals, other dimensions, and powerful experiments. Online, these statements were often presented as if a CERN insider had admitted something extraordinary. But when we look carefully, we see a difference between speculation and published physics. Scientific research at CERN is public. The data is reviewed by thousands of physicists around the world. Papers are published, results are debated openly, experiments are repeated and analyzed by independent groups. There is no secret hidden lab, separate from the main Collider experiments, where unknown realities are being torn open. Now here's a gentle question. If CERN were doing something as dramatic as opening portals or destabilizing reality, would it remain hidden? The Collider involves thousands of scientists from over 100 countries. Universities across the world analyze the data. The detectors themselves are so large, as tall as multi-story buildings, and weighing as much as thousands of cars, that their construction required global collaboration. It's not a small private lab. It's more like a scientific city. For something extraordinary and dangerous to occur, thousands of people would have to remain silent. Across languages, across cultures, across decades, history shows us that large secrets involving thousands of people are nearly impossible to keep. Information leaks, whistleblowers appear, documents surface. But what we see from CERN is not silence, it's constant publication. So why do viral claims spread so quickly? Part of it is the way short clips work online. A 10-second segment of a longer interview can sound far more dramatic than the full conversation. Tone shifts, context disappears, viewers fill in the gaps, and once a dramatic interpretation forms, it spreads. It spreads because it feels important, because it feels like uncovering hidden truth, because it transforms a complex physics experiment into a story of power and secrecy. But science moves differently. When physicists talk about higher dimensions or new physics, they are speaking carefully. They mean deviations in data, slight statistical anomalies, patterns that require years of checking. They do not mean cinematic events. It's also worth noting something comforting. The safety of the Large Hadron Collider has been reviewed not just internally, but by independent scientists worldwide before it ever began operating. Detailed reports examined every hypothetical risk, including black holes, vacuum decay, strange matter, and more. These reports were published openly. They compared collider energies to natural cosmic rays that strike Earth constantly. Particles with even higher energy that have been hitting our planet for billions of years. If those natural events have not destroyed Earth, the collider's controlled collisions will not either. So when someone online suggests that CERN is doing something hidden or dangerous, it helps to ask, is this claim supported by peer-reviewed evidence? Or is it built on interpretation and speculation? Speculation is not inherently wrong. Curiosity is good. Questioning is healthy. But extraordinary claims require extraordinary evidence. And so far, there is no verified scientific evidence that CERN has opened portals, shifted timelines, or altered reality. There are thousands of research papers analyzing particle behavior. There are measurements of bosons, quarks, and decay patterns. There are graphs and charts and error margins, not rifts in space. Sometimes, when we hear confident statements from a single voice, it feels compelling. But science is not built on single voices. It is built on community verification. Imagine building a bridge. You would not rely on one engineer's opinion alone. You would require teams, stress tests, simulations, inspections. CERN operates in a similar way. Every result is checked, every conclusion is questioned, and disagreements are debated openly. That is how science protects itself from error. So when viral claims circulate, whether from Dr. Stuckelberger or anyone else, it helps to gently separate two things: personal interpretation and collective scientific evidence. One can be passionate and dramatic. The other moves slowly, carefully, and publicly. And in the case of CERN, the public record shows a research institution trying to understand the smallest pieces of matter, not a hidden project trying to break the universe. It's natural to feel intrigued by bold claims. They add color to the story. They make the unknown feel alive. But sometimes, the quiet truth, thousands of scientists analyzing tiny particle traces deep underground, is far more grounded and far more reassuring. As we continue, we'll explore what physics itself actually allows, beyond headlines, beyond speculation, and what reality even means at its deepest level, because the universe is already strange enough, and we haven't even reached its most fascinating parts yet. As conversations about CERN spread online, another type of voice began to appear. Not a scientist working inside a large collaboration, not a published researcher writing technical papers, but a young thinker speaking confidently about the nature of reality itself. One name that often comes up is Max Lowen. In interviews and online videos, he has spoken about the universe as energy, about consciousness, about vibrations and frequencies. He speaks in a way that feels bold and certain. And when someone speaks with certainty about big questions, it naturally draws attention, especially when the topic is something as mysterious as reality itself. You may have heard statements like, "Everything is energy," or "Reality is just vibration." These phrases sound profound. They feel like they reveal something hidden. But what do they actually mean? In physics, it is true that matter and energy are deeply connected. Einstein's famous equation, E = mc squared, tells us that mass is a form of energy. In simple terms, matter can be converted into energy, and energy into matter. That sounds dramatic, and it is. But it doesn't mean that reality is fragile or easily reshaped by thought or by particle collisions. When physicists say something is energy, they are describing measurable quantities. Energy has units. It can be calculated. It can be transferred. It follows strict rules. It is not a vague spiritual force. So when someone says, "Reality is energy," a gentle question helps. In what sense? If they mean that all matter has energy and obeys physical laws, that is correct. If they mean that reality is flexible and can be torn open like a curtain, that is a different claim entirely. Sometimes philosophical speculation gets blended with experimental physics. Philosophy asks big questions. What is existence? What is consciousness? Is reality fundamentally mental or physical? Physics asks more focused questions. How do particles behave? What forces act between them? What patterns appear in experiments? Both are valuable, but they operate in different ways. The Large Hadron Collider does not test philosophical ideas about consciousness shaping reality. It tests particle interactions. It measures how often certain particles appear after collisions. It records decay patterns that last for less than a trillionth of a second. It compares those results to mathematical predictions. It is precise. It is technical. It is grounded in measurable outcomes. Now here is something interesting. Quantum physics, the study of very small particles, is often described as strange. People hear about wave-particle duality or quantum uncertainty and feel that reality must be unstable. For example, in some experiments, particles behave like waves. In others, they behave like particles. That sounds confusing at first. So the natural question is, does this mean reality is fuzzy or breakable? The answer is calmer than it seems. Quantum behavior follows mathematical rules with incredible precision. The strangeness comes from the fact that the microscopic world doesn't behave like everyday objects. An electron does not orbit an atom the way the moon orbits Earth. It exists as a probability cloud, more like a blurred region where it is likely to be found. But that does not mean it randomly disappears into other universes because of a machine underground. It means nature is subtler than our daily experience. When online voices blend quantum language with big philosophical claims, it can sound like hidden knowledge. Words like frequency, vibration, and energy create a feeling of depth, but physics uses these words with strict definitions. Frequency means how often something oscillates per second, like how many times a guitar string vibrates in 1 second to produce a note. Vibration means motion around a position, like a swing moving back and forth. Energy means the ability to do work. It can be measured in joules. These are not mystical ideas. They are measurable properties. So when someone suggests that CERN might disrupt reality because everything is energy, we can gently ask, what specific physical mechanism would cause that disruption? Physics requires clear cause and effect. If you increase energy in a collision, certain particles may appear. If you decrease it, they may not. The results are predictable within known laws. The collider does not interact with consciousness. It does not send vibrations through the universe in a way that alters timelines. It studies extremely small distances far smaller than atoms, and extremely short times shorter than light traveling across a speck of dust. There is a difference between poetic description and experimental science. Poetry can say, we are made of stardust and energy, and that is beautiful and true in a broad sense. Science says, protons have a specific mass and charge, and their interactions follow quantum field equations. Both perspectives can coexist, but when we confuse them, we can begin to imagine dangers that are not supported by physics. It's natural to feel drawn to bold ideas. They make the universe feel alive and dramatic. But the real wonder is this: even without portals or timeline shifts, reality is already astonishing. The fact that particles can behave as waves, the fact that empty space is not truly empty, but filled with quantum fields, the fact that tiny fluctuations in the early universe grew into galaxies billions of light years wide, galaxies so large that light takes millions of years just to cross them, those are real mysteries. And they do not require us to believe that CERN is tearing open existence. They show that existence is already deeper and more layered than it appears. So when we hear confident voices claiming that reality is energy and therefore fragile, it helps to slow down. Energy in physics is structured. It follows laws, And those laws have held steady across the entire visible universe, across distances so vast that light, traveling at 300,000 kilometers per second, takes billions of years to cross them. That stability is not easily shaken, not by philosophy, not by speculation, and not by a circular machine underground, carefully measuring the smallest pieces of matter. The universe may be subtle, but it is not fragile in the way rumors suggest. And as we continue, we will look more closely at what physics truly allows, and what reality really means when examined at its deepest level. When people ask whether CERN could tear a hole in reality, there is a deeper question hiding underneath. What is reality exactly? It sounds simple at first. Reality is the world around us, the floor beneath your feet, the air you breathe, the sound of distant traffic, or the quiet hum of a room at night. But when physics looks closely, reality becomes something far more subtle. Let's start with something solid. Imagine a wooden table. It feels firm, stable. You can knock on it and hear the sound. It seems continuous. But if you could zoom in, far beyond what any normal microscope can show, you would see atoms. And if you zoomed in further, inside those atoms you would see mostly empty space. The nucleus at the center of an atom is incredibly small compared to the atom itself. If an atom were the size of a large sports stadium, the nucleus would be about the size of a marble sitting at the center. Everything else would be empty space where electrons move. So already what feels solid is mostly space. Now go deeper. Inside the nucleus are protons and neutrons. Inside protons and neutrons are quarks. And beneath even that level, modern physics describes something even more fundamental: fields. According to quantum field theory, the universe is made not just of particles, but of fields that exist everywhere. Imagine the surface of a calm lake stretching as far as you can see. That lake represents a field. When a small ripple forms on the surface, that ripple is like a particle. In this view, an electron is not a tiny solid bead floating in space. It is a tiny vibration in an electron field that fills the entire universe. That idea alone changes how we see reality. You are not made of tiny marbles glued together. You are made of patterns of vibration in invisible fields that stretch across space. And these fields are not fragile like glass. They are woven into the structure of the universe itself. Another layer of reality is space-time. We often think of space as an empty stage where events happen, and time as a separate ticking clock. But Einstein showed that space and time are connected. They form a four-dimensional fabric called space-time. Mass and energy bend this fabric. If you place something heavy on a mattress, it dips. Smaller objects roll toward the dip. That bending is similar to how gravity works. Space-time bends around planets, stars, and galaxies. This bending is not easy to disrupt. To significantly tear or distort space-time, you would need enormous energy. Not the energy of a laboratory machine, not even the energy of all human technology combined. You would need something closer to the energy released when massive stars explode. Events so bright they can outshine entire galaxies for a short time. And even those explosions do not tear reality apart. They bend space-time locally. Then the universe continues. Now here's a gentle question. If reality is made of fields and space-time, could smashing particles disrupt those fields permanently? In everyday life, if you strike water, it splashes, but the lake does not disappear. The surface ripples, then settles. Particle collisions are like tiny splashes in quantum fields. They create ripples, short-lived particles that appear and vanish in less than a trillionth of a second. But the fields themselves remain. They are not fragile membranes. They are more like the underlying fabric that defines existence. There is also something called vacuum fluctuations. When we imagine empty space, we picture nothing, a perfect void. But in quantum physics, Even empty space is active. Tiny particle-antiparticle pairs briefly appear and disappear everywhere, all the time. This activity happens naturally, constantly, throughout the universe. The LHC does not create vacuum fluctuations from scratch. They are already part of reality. So when someone asks whether CERN could tear a hole in reality, we must first understand that reality is not a thin wall. It is a deeply stable system of fields and laws that have governed the universe for about 13.8 billion years. That's 13.8 billion trips of Earth around the Sun. Imagine counting each year one by one. You would never reach that number in a lifetime. For all that time, stars have formed and died, galaxies have collided, black holes have merged, sending gravitational waves across space. And yet, the fundamental structure of reality has remained consistent. The same physical constants apply here as they do in distant galaxies billions of light years away. Light travels at the same speed everywhere. Electrons have the same charge everywhere. Gravity behaves the same way everywhere we have measured it. That stability is remarkable. It suggests that reality is not easily torn. Even the Big Bang, the event that marked the beginning of our observable universe, did not tear reality in the sense of breaking something pre-existing. It was the rapid expansion of space-time itself. Reality did not shatter. It unfolded. So perhaps the better question is not whether CERN could tear reality, but what reality truly is. It is not a fragile surface. It is a dynamic but stable system of fields and space-time, governed by consistent laws. Those laws allow for astonishing phenomena. Quantum entanglement, where particles separated by vast distances behave in connected ways. They allow for stars so large that millions of Earths could fit inside them. They allow for galaxies so wide that light takes over 100,000 years to cross them, longer than all of recorded human history. Reality is already extraordinary, and the Large Hadron Collider, rather than breaking it, is simply tapping gently on its surface, listening for echoes, not tearing the fabric, just trying to understand its weave. And as we continue, we will explore whether those echoes could ever grow loud enough to truly threaten the structure of existence, or whether the universe is far more resilient than we imagine now that we have a clearer picture of what reality means in physics. Fields, space-time, stable laws. We can return to the central worry. Could particle collisions inside the Large Hadron Collider actually damage space-time? It's an understandable concern. When you hear that protons are being smashed together at nearly the speed of light, it sounds violent, dramatic, almost cosmic. But let's slow down and compare scales carefully. Inside the LHC, protons are accelerated to extremely high speeds. Each proton carries energy measured in trillions of electron volts. That sounds enormous. Trillions. But numbers can be misleading when they're detached from comparison. In everyday terms, the energy of a single proton collision in the LHC is roughly comparable to the kinetic energy of a flying mosquito. Yes, that's small. The reason physicists call it high energy is because that energy is concentrated into something unbelievably tiny, a particle far smaller than an atom. It's like focusing the force of a gentle tap onto the tip of a needle. The pressure at that tiny point can be intense, but the total energy involved is modest. Now here's where the comparison becomes powerful. Every single day, Earth is struck by cosmic rays from space. These are high-energy particles traveling through the universe at incredible speeds. Some of them carry far more energy than the protons in the LHC. In fact, the highest energy cosmic rays ever recorded have energies millions of times greater than those produced in the collider. Millions of times greater. And they don't just strike Earth occasionally. They have been striking Earth constantly for billions of years. Long before humans existed, long before mammals existed, even before complex life formed in the oceans. So here's the gentle question. If high-energy particle collisions could tear space-time, wouldn't cosmic rays have done it already? Cosmic rays collide with particles in our atmosphere at energies higher than the LHC can achieve. They produce particle showers that cascade through the sky. These natural collisions are not controlled. They are not shielded. They happen across the entire planet. And yet, space-time remains intact. The Earth still orbits the Sun. The Moon still circles the Earth. Gravity behaves the same way today as it did millions of years ago. The laws of physics remain steady. This comparison is one of the strongest reassurances physicists offer. The universe has already been running experiments far more energetic than ours, for far longer than humanity has existed. If tearing space-time were easy, nature would have done it first. Now, someone might ask, but what if the LHC creates a special kind of collision that cosmic rays don't? It's a fair question. Cosmic rays usually hit stationary particles in the atmosphere. In the LHC, two beams of protons collide head-on. That setup allows physicists to focus energy more precisely. But even accounting for this difference, the total energy involved is still tiny compared to cosmic events. Let's think about space-time itself. To significantly distort space-time, you need enormous mass or energy. The Sun bends space-time enough to hold planets in orbit. A black hole bends it so strongly that not even light escapes. These are objects with masses beyond everyday imagination. The LHC, by contrast, contains energy in tiny particles. Even though those particles move incredibly fast, their mass is so small that the total energy is nowhere near what would be required to warp space-time dramatically. It's like comparing a single spark to a lightning storm. Both involve electricity, both involve energy, but their scale and impact are completely different. Another way to picture it: imagine tapping lightly on a thick steel bridge with your finger. You can create a tiny vibration, but you cannot break the bridge. The structure is too strong, too massive. Space-time is more like that bridge than like thin glass. It can ripple, produced when massive black holes collide, travel through space-time like gentle ripples through water. These waves were detected by instruments so sensitive they can measure changes smaller than the width of a proton. Even those enormous cosmic events, involving black holes heavier than dozens of suns, do not tear space-time apart. They create waves that pass through, and the fabric remains. So when we think about particle collisions inside the LHC, we must hold on to perspective. Yes, they are impressive feats of engineering. Yes, they probe conditions similar to those a tiny fraction of a second after the Big Bang. But they do so on an incredibly small scale. The energy is localized, the events are microscopic, and the universe itself has already demonstrated resilience under far greater forces. Sometimes fear grows when we isolate a fact from its context. Protons collide at near light speed. That sounds alarming on its own. But when we add cosmic rays collide at even higher energies every day, the picture changes. And when we add space-time withstands the merging of black holes billions of times more energetic, the fear softens further. Reality is not brittle porcelain. It is more like a vast ocean. You can toss a pebble and create ripples, but you cannot shatter the sea. The LHC tosses pebbles into the quantum ocean. Tiny ripples appear. Data is collected, and the ocean remains. So the question shifts. If particle collisions cannot break space-time, then what would it actually take to disrupt reality at its deepest level? That question leads us toward energy scales far beyond anything humanity can currently produce. And as we move there, we begin to see just how far away we are from even approaching the true limits of the universe. If we continue following the question, could CERN ever reach the kind of power needed to truly disturb reality? We arrive at something physicists call an energy scale. An energy scale is simply the level of energy at which certain physical effects become important. For example, Water behaves calmly at room temperature, but if you heat it to 100 degrees Celsius, about the temperature of boiling water in a kitchen pot, it changes state. It turns into steam. The behavior shifts because you crossed a certain energy threshold. In physics, different phenomena appear at different energy scales. Atoms break apart at one scale, atomic nuclei break apart at a higher one. And then there is a much, much higher scale called the Planck energy. This is the scale where our current understanding of physics, quantum mechanics, and general relativity is expected to merge into something deeper. It's the level where space-time itself might behave in unfamiliar ways. So naturally, someone might ask, how close is the Large Hadron Collider to that Planck scale? The answer is simple and calming. Not even remotely close. The Planck energy is about 10 to the power of 16 times higher than the energies reached at the LHC. That number is hard to picture, so let's compare it. Imagine the LHC's highest energy as the height of a small ant, just a few millimeters tall. Now imagine the Planck energy as a mountain towering kilometers into the sky. The difference between them is not small. It's like comparing a single grain of sand to an entire beach, stretching for miles. Or like comparing the energy needed to lift a book off a table to the energy released by the sun every second, which is so enormous it could power human civilization for billions of years. The Planck scale is where space-time itself might become quantized, meaning it might have a smallest possible unit, like pixels on a screen. But we are nowhere near that level. The LHC operates at energies that allow us to study known particles and test theories within the standard model of physics. It can probe deep into the structure of matter. It can recreate conditions similar to a tiny fraction of a second after the Big Bang, but only in terms of temperature and particle density, not in total energy. That distinction matters. When physicists say the collider recreates early universe conditions, they mean in a very small region, for a very short time, not on a cosmic scale. Let's think of it like this. If you light a match in a dark field, you create a tiny region that is hot and bright. But you have not recreated the sun. You have not changed the sky. You have simply produced a small spark in a controlled space. The early universe was unimaginably dense and energetic everywhere. The LHC recreates something similar in a space smaller than an atom, and for a time shorter than a blink. That's a huge difference. Another way to see the gap is through temperature. The LHC collisions briefly reach temperatures around a few trillion degrees Celsius. That sounds enormous, and it is. But again, this temperature exists in a region far smaller than anything we can see, and only for an instant. The Planck temperature, associated with the Planck energy, is about 10 to the power of 32 degrees Celsius. That is a 1, followed by 32 zeros. If a trillion degrees is like the heat of a powerful furnace, the Planck temperature is beyond any comparison in everyday life. It is so extreme that our current laws of physics cannot fully describe it. We are nowhere near that level. Not by a small margin. By a gap so large it's almost impossible to bridge. So when people worry that CERN might accidentally push reality into unknown territory, they are imagining that the collider is operating near the edge of physics. But it isn't. It's operating within a well-tested range. It pushes boundaries carefully, but those boundaries are still far from the deep foundations where space-time itself might behave unpredictably. And here's another calming thought. If reaching the Planck scale required building a machine even slightly larger than the LHC, scientists might worry. But to reach it directly, you would need something far beyond anything humanity can currently engineer. A machine so powerful and vast that it would dwarf our greatest structures. The LHC's 27-kilometer ring, already as long as crossing a city, would seem tiny compared to what would be required. It would be like comparing a bicycle to a spacecraft capable of crossing galaxies. So the energy scale problem is simple. The energies required to truly alter space-time are unimaginably high. The energies produced by the LHC are impressive, but modest in cosmic terms. And nature itself regularly performs experiments at energies higher than ours, through cosmic rays and astrophysical events, yet space-time remains stable. The stars continue burning, galaxies continue rotating, the laws remain consistent. Reality is not perched at the edge of collapse. It is held together by constants and forces that have remained steady across billions of years and billions of light years of distance. So as we gently move forward, we can let that perspective settle. CERN is powerful by human standards, but by cosmic standards, it is a small, careful probe. And the true foundations of reality, if they can even be shaken, lie at energies far beyond our reach, far beyond a ring beneath Switzerland, far beyond anything we can currently imagine building. And that distance, in itself, is deeply reassuring. There is one idea that sounds far more unsettling than portals or wormholes. It's called vacuum decay. And unlike many internet rumors, this idea actually comes from real physics. But before it becomes frightening, let's gently unpack what it means. In everyday life, when we say vacuum, we mean empty space, a place with nothing in it. But in quantum physics, empty space is not truly empty. It has energy, it has fields, it has structure. And here's where it gets interesting: the vacuum we live in. The lowest energy state of the universe as we know it might not be the absolute lowest possible state. It might be what physicists call a false vacuum. Imagine a ball resting in a shallow dip on a hillside. It feels stable. It doesn't roll away, but somewhere nearby there might be a deeper valley. If something nudges the ball hard enough, it could roll into that deeper valley. That shift would represent a change in the vacuum state. Now here's the unsettling part. If the vacuum of the universe were to shift to a lower energy state, the laws of physics could change instantly. The masses of particles might shift. The forces might behave differently. And this change would spread outward at the speed of light. No warning. No time to react. It sounds terrifying. So naturally, someone might ask, could the Large Hadron Collider trigger this? The answer, based on current physics, is no. And the reason connects back to something we've discussed before: cosmic rays. If vacuum decay were possible at the energy levels reached by the LHC, it would have already happened. Cosmic rays strike Earth with energies far higher than those produced in the collider. They also strike the Moon, the Sun, and countless other objects throughout the universe. These collisions have been happening for billions of years. That's billions of years of natural high-energy experiments. If those energies were enough to push the vacuum into a lower state, the transition would have occurred long before humans ever existed. The universe would have already shifted, but it hasn't. The constants of physics, like the strength of electromagnetism and the mass of the electron, remain steady across vast distances. Light from galaxies billions of light years away behaves according to the same rules as light here on Earth. That consistency is powerful evidence that we are not perched on the edge of a fragile vacuum state, waiting to collapse from a small disturbance. Now, it's true that some theoretical calculations suggest our vacuum might be metastable, meaning stable for an extremely long time, but not absolutely permanent. But extremely long time in physics often means far beyond human comprehension. Some estimates suggest that if vacuum decay were possible, it might take longer than the current age of the universe, which is about 13.8 billion years. To picture that, imagine counting 1 year per second. You would need more than 400 years just to count to 13.8 billion. And that's just the universe's current age. Vacuum decay, if it were to happen naturally, might require time spans far longer than that. So could a human-made experiment trigger it early? Physics suggests no, because again, nature already performs higher energy collisions regularly. Let's return to the ball on the hill picture. If small disturbances could push the ball into the deeper valley, then natural disturbances would have done so long ago. The LHC is not introducing a new type of energy into the universe. It's recreating energies that have already existed in cosmic events countless times. Another calming thought is this: theoretical discussions about vacuum stability are based on extrapolating known physics to extreme conditions. But our knowledge is incomplete. There may be stabilizing factors we don't fully understand yet. Additional fields, hidden mechanisms, unknown symmetries. Science continues to refine these calculations. But so far, nothing indicates that current collider energies pose a realistic risk. It's also important to remember that the vacuum, in quantum field theory, is not like a delicate bubble. It is the lowest energy configuration of fields across the universe. Changing it would require not just local energy, but altering the global structure of those fields. That's not something a brief microscopic collision can accomplish. It would be like trying to change the shape of an entire ocean by dropping a pebble. Yes, the pebble creates ripples, but the ocean remains. So why does the vacuum decay idea feel so intense? Because it's subtle. Because it doesn't involve visible destruction like a black hole swallowing the Earth. It involves the underlying rules of reality shifting instantly. That kind of idea touches something deep. It reminds us that our existence depends on delicate balances, the precise strengths of forces, the exact masses of particles. But delicate does not mean fragile in the everyday sense. Those balances have survived supernova explosions, galaxy collisions, and cosmic radiation for billions of years. They are not easily disturbed. And here's something quietly reassuring. Physicists did not ignore vacuum decay when planning the LHC. It was studied, calculated, published. The conclusion was clear. If the collider could trigger such a transition, the universe would already have done so naturally. And since we are still here, breathing, listening, thinking, it seems that reality is more stable than our fears suggest. Vacuum decay remains an interesting theoretical question, but it is not a looming threat beneath a 27-kilometer ring underground. It is part of the deeper mystery of why the universe has the properties it does. And that mystery is vast, calm, and still unfolding. We've already touched on microscopic black holes, but it's worth slowing down and looking at this idea more carefully, because when people hear the words black hole and laboratory in the same sentence, it triggers something deep. Black holes belong in deep space, near collapsing stars. They belong at the centers of galaxies where gravity is so strong that even light cannot escape. They do not belong under the border of Switzerland and France. So let's gently ask again, if a microscopic black hole formed inside the Large Hadron Collider, what would really happen? First, we need to picture how small we're talking. Not small like a grain of sand, not small like a bacterium, not even small like an atom. We're talking about something far smaller than a proton. If a proton were enlarged to the size of a basketball, this hypothetical black hole would still be far smaller than a speck of dust floating in the air. It would not be a dark sphere drifting through the tunnel. It would be a tiny, almost unimaginable point of concentrated energy. Now here's the key idea. Hawking radiation. Stephen Hawking proposed that black holes are not completely stable. They slowly lose mass by emitting radiation due to quantum effects near their edges. For massive black holes, the kind formed by collapsing stars, this evaporation process is extremely slow. So slow that it would take longer than the current age of the universe for one to disappear. But the smaller the black hole, the faster it evaporates. And at microscopic scales, that evaporation becomes almost instant. A tiny black hole with the mass possibly created in a collider, if such a thing were even theoretically allowed, would vanish in a time so short it's difficult to express, shorter than the time it takes light to travel across a single atom. In other words, it would appear and disappear before it could interact meaningfully with anything around it. So here's the natural question. Could it grow instead of evaporate? For growth to happen, it would need to pull in nearby matter faster than it radiates energy away. But gravity at that tiny scale would be unbelievably weak. Even though black holes have strong gravity relative to their size, a microscopic one would not have the mass to significantly attract surrounding particles. Remember, gravity depends on mass. The Earth's gravity feels strong because the Earth weighs about 6 billion trillion kilograms. That's like stacking billions of mountains together. A microscopic black hole created from particle collision energy would weigh about as much as a single proton. Unimaginably tiny. Its gravitational pull would be far weaker than the electromagnetic forces holding atoms together. It wouldn't suck in nearby matter like a vacuum cleaner. It wouldn't even pull in a single atom before evaporating. And once again, we return to cosmic rays. High-energy particles from space strike Earth's atmosphere every day with energies higher than those achieved in the LHC. If microscopic black holes could form and grow dangerously, these cosmic collisions would have triggered that process long ago. But the Earth remains, the Moon remains, the Sun remains, and they have endured billions of years of cosmic bombardment. Another calming detail is that if stable microscopic black holes could exist and grow, dense astronomical objects like neutron stars would be vulnerable. Neutron stars are incredibly compact. Imagine squeezing the mass of the Sun into a sphere about 20 kilometers across, roughly the size of a small city. If stable micro-black holes could form naturally from cosmic rays, they would likely have consumed neutron stars over cosmic time. But we observe neutron stars still shining, still spinning. That observation alone provides strong reassurance. Physics does not operate in isolation from the rest of the universe. Any theory about dangerous black holes must match what we see in nature. And what we see tells us that high-energy particle collisions are not catastrophic. It's also helpful to remember that scientists at CERN openly studied these scenarios before the collider began operating. They examined black hole formation in detail. They compared collider energies to cosmic ray events. They published safety reports. The conclusion was not rushed. It was carefully reasoned, and it was supported by decades of observation. Sometimes fear grows because the word black hole feels final. It feels like the ultimate symbol of destruction. But the universe is more nuanced. A black hole the mass of our sun is terrifying. A black hole with the mass of a proton is fleeting, like a spark that flashes and vanishes before you can blink. Scale transforms danger into harmlessness. And in this case, the scale difference is enormous. The LHC does not concentrate enough mass to create a lasting gravitational trap. It concentrates energy into tiny regions for tiny moments, revealing patterns that help us understand how matter behaves. It is not a machine designed to create cosmic objects. It is a microscope, a very large, very sophisticated microscope, aimed at the smallest pieces of reality. So when we imagine black holes forming in a laboratory, it helps to replace the cinematic image with the physical one. Not a swirling void, not a growing sphere, but a fleeting quantum ripple, if it exists at all. A ripple that fades almost instantly. The universe has tested far greater energies than ours, and it remains steady. Black holes belong to collapsing stars and merging galaxies. Events so powerful they shake space-time itself. They do not belong to controlled particle collisions deep underground. And the more we understand their scale, the calmer the picture becomes. Because the physics is not dramatic, it is precise. And it is deeply reassuring. The idea of extra dimensions has a special kind of pull on the imagination. It sounds like hidden rooms in the universe, secret layers folded just out of sight, doorways waiting to be opened. So when people hear that scientists at CERN are searching for signs of extra dimensions, it can feel like they are probing the walls of reality itself. But what do physicists actually mean by extra dimensions? In everyday life, we move through 3 dimensions of space: forward and backward, left and right, up and down, and we experience time as a 4th dimension, flowing steadily forward. That's the world we know, but some advanced theories, especially certain versions of string theory, suggest that the universe might include additional spatial dimensions beyond the 3 we experience. That sounds enormous, so the natural question appears: if extra dimensions exist, where are they? Why don't we see them? The answer proposed by these theories is subtle. The extra dimensions, if they exist, are not large open spaces extending in new directions. They are thought to be compactified, curled up so tightly that they are incredibly small. To picture this, imagine standing on a long, straight road that stretches to the horizon. From far away, the road looks one-dimensional, just a line. But if you kneel down and look closely, you see the width of the road. You can move side to side, as well as forward and backward. Now imagine something even smaller, like a tightrope. From a distance, it looks like a thin line, but an ant crawling on it would experience not only the length of the rope, but also its circular surface. The rope has an extra dimension around its circumference, but it is tiny compared to its length. In some theories, extra dimensions are like that tiny circular surface, but at scales far smaller than atoms. We're talking about lengths near something called the Planck length, about 10 to the minus 35 meters. That number is almost impossible to grasp. If an atom were enlarged to the size of the Earth, the Planck length would still be far smaller than a grain of sand on that Earth-sized atom. That's how tiny we're talking. So when scientists look for extra dimensions at the LHC, they are not trying to open doors. They are searching for small deviations in particle behavior that might hint at their existence. For example, if gravity could leak into extra dimensions, we might observe tiny differences in how energy is distributed in collisions. These would not be visible distortions in space. They would be subtle patterns in data, small missing amounts of energy that cannot be accounted for by known particles. It's very different from the idea of punching through into another universe. Extra dimensions, if real, would be woven into the structure of space itself. They would not be separate rooms waiting behind thin walls. They would be like additional directions curled tightly at every point in space. So here's a gentle question. If extra dimensions are that small, could the LHC somehow enlarge them? The answer, according to our current understanding, is no. Dimensions are not objects you can stretch like rubber bands. They are part of the mathematical framework describing space-time. To alter them would require energy scales far beyond anything we can produce, far beyond even cosmic ray collisions. And again, nature already performs experiments at higher energies than ours. If high-energy collisions could expand or open extra dimensions, cosmic rays would have done it long ago. But we see no evidence of dimensions unfurling across the sky. The laws of physics remain stable. Gravity behaves consistently. Light travels at the same speed. The universe does not flicker or shift. Another point worth considering is that string theory itself remains unproven. It is a mathematically rich framework, but we have not yet observed definitive experimental evidence for its extra dimensions. So CERN is not operating under the assumption that extra dimensions are definitely there. It is testing whether there are any signs of physics beyond the standard model. That's careful exploration, not reckless probing. It's also important to understand that extra dimensions in these theories are not places filled with alternate versions of ourselves. They are geometric features of space-time. They do not contain cities or stars. They are not parallel worlds in the science fiction sense. They are mathematical structures. So when someone imagines CERN opening a gateway to another dimension, it helps to gently return to what dimensions mean in physics. They describe directions in which movement or variation can occur. They are not rooms. They are not tunnels. They are part of the deep geometry of the universe, and that geometry has been stable for billions of years. If extra dimensions exist, they have existed since the earliest moments of the universe. They are not newly created by human machines. They are part of the cosmic blueprint. The LHC is simply asking whether there are faint clues that such dimensions might be present. It is listening for echoes in data, not prying open hidden spaces. And perhaps the most calming thought is this: even if extra dimensions exist, they are not threats. They are features. They are part of the elegance and complexity of reality. Understanding them would not tear the universe apart. It would deepen our knowledge of how it holds together. Because the goal of CERN is not to break the structure of existence. It is to understand its shape. And the shape, however complex, appears far more resilient than our fears suggest. By now, we've explored black holes, wormholes, vacuum decay, extra dimensions and cosmic energy scales. Each time the pattern has been similar. The idea sounds dramatic at first, but when we look closely at the physics and compare scales, the fear softens. So let's step back and ask a simple question. Why are scientists so confident that CERN is safe? Before the Large Hadron Collider was ever switched on, detailed safety studies were carried out. Not quietly, not secretly, publicly. Teams of physicists examined every scenario that had been proposed. Microscopic black holes, strange matter, vacuum decay, exotic particles. They wrote reports. They published their reasoning. Independent scientists reviewed their conclusions. This wasn't a rushed decision. The collider took decades to design and build. The tunnel alone stretches 27 kilometers, about as long as driving from one side of a major city to the other. It required international cooperation, billions of dollars, and years of engineering. You don't invest that level of global collaboration without carefully checking the risks. One of the strongest arguments for safety keeps returning. Cosmic rays. These high-energy particles from space collide with Earth's atmosphere constantly. Some carry energies higher than those produced in the LHC, not slightly higher, in some cases far higher. And they've been doing this for billions of years. Think about that. For longer than dinosaurs existed, for longer than mountains have stood, for longer than complex life has walked the Earth. If any of the catastrophic scenarios were possible at LHC energy levels, natural cosmic collisions would have triggered them already. But the planet remains intact, the moon remains intact, the sun remains stable. That comparison is not a guess. It's based on measurable energy levels. The LHC reaches energies of around 14 trillion electron volts per collision. That sounds huge, but some cosmic rays carry millions of times more energy. Nature has been running experiments at higher energies than ours since long before humanity appeared. So when people imagine CERN as pushing reality into dangerous territory, it helps to remember that we are not crossing a new cosmic boundary. We are recreating in controlled form what already happens naturally. Another reassuring factor is oversight. CERN is not operated by a single hidden group. It involves thousands of scientists from over 100 countries. Universities around the world analyze its data. Research papers are published openly. If something unexpected and dangerous appeared in the data, it would not be confined to one building. It would be visible to the global scientific community. Large collaborations make secrecy harder, not easier. And science itself is built on questioning results. If one team claims something unusual, other teams attempt to reproduce or challenge it. That constant scrutiny acts as a safety net. There's also the physical structure of the machine itself. The collider's powerful magnets are cooled to temperatures colder than outer space, about minus 271 degrees Celsius, just above absolute zero. That's colder than the dark vacuum between stars. Why so cold? Because at those temperatures, certain materials become superconducting, allowing electricity to flow with almost no resistance. This extreme cooling is an engineering necessity, not a sign of instability. The beams of protons circulate inside narrow vacuum pipes. If something goes wrong, systems are designed to safely dump the beams into special absorbers. In other words, there are layers of control. It's not a chaotic device running out of supervision. It's one of the most carefully monitored machines ever built. So why does the internet often portray it as dangerous? Part of the answer lies in human psychology. Big machines feel powerful. Underground facilities feel secretive. Scientific language feels mysterious. When something is large, hidden from everyday view, and described in unfamiliar terms, it becomes easy to project fear onto it. Imagine seeing a massive power station for the first time, with tall cooling towers and humming equipment. Without understanding how it works, it might look intimidating. But once you learn the principles, steam turbines, generators, safety valves, the fear fades. Knowledge replaces mystery. The same applies to CERN. When you understand that it accelerates tiny particles and measures their collisions, the dramatic imagery of portals and tears in space-time begins to feel misplaced. There is also something else worth considering. If scientists believed there was even a small realistic chance of catastrophic vacuum decay or runaway black holes, they would not proceed lightly. Physicists are not immune to fear. They live on this planet too. They have families. They breathe the same air. The idea that thousands of researchers would casually risk global destruction without overwhelming evidence of safety does not match how science operates. Scientific caution is built into the culture. Experiments are tested at lower energies before higher ones. Systems are upgraded carefully. Results are reviewed repeatedly. CERN did not simply turn on at full power without gradual steps. It increased energy levels over time, monitoring behavior at each stage. That's not recklessness, that's caution. So when we step back and look at the full picture, cosmic ray comparisons, energy scale gaps, safety reviews, international oversight, the image changes. CERN is not a reckless machine probing forbidden territory. It is a carefully designed tool, built to explore the smallest building blocks of matter within well-understood limits. The internet thrives on dramatic possibilities. Scientists' open portal spreads faster than particle scattering matches theoretical prediction. But drama does not equal danger, and mystery does not equal threat. The universe has endured forces far greater than anything humanity can produce, and the Large Hadron Collider, impressive as it is, operates comfortably within that vast margin of safety. Reality is not trembling at its edges. It is being studied, measured, and understood a little more deeply each day. Even after hearing the physics, even after comparing energy scales and cosmic rays, a quiet feeling can remain. A machine that large, doing something that advanced, deep underground. It just feels unsettling. And that feeling is important, because sometimes the fear around CERN isn't really about equations or vacuum decay. It's about scale. Human beings are not used to machines that stretch 27 kilometers in a perfect circle beneath the Earth. That's about the distance you might drive during a long commute across a city. To imagine that entire loop hidden underground, filled with magnets colder than deep space, guiding particles at nearly the speed of light. It feels almost mythic. Throughout history, large new technologies have triggered similar reactions. When the first trains were introduced, some people feared that traveling at high speeds that today feel slow, would harm the human body. Early locomotives moved at around 30 miles per hour. At the time, that seemed extreme. Some worried that passengers might suffocate or that their organs couldn't handle such velocity. Today, cars routinely move faster than that, and airplanes travel at hundreds of miles per hour without issue. When electricity was first installed in cities, it felt dangerous and mysterious. Wires ran through walls. Invisible forces powered lights, people worried about unseen risks. When radio towers rose into the sky, some believed they might disrupt the atmosphere. Each time the pattern was similar. A new powerful technology appears. It operates in ways that are invisible to everyday experience. It feels larger than what came before, and fear fills in the unknown spaces. CERN fits this pattern. It is one of the largest scientific machines ever built. Its magnets are cooled to temperatures colder than outer space, about -271 degrees Celsius, just a breath above absolute zero. That's colder than the dark regions between stars. Its detectors are as tall as 5-story buildings and weigh as much as thousands of cars stacked together. And it deals with particles too small to see, moving at speeds close to the speed of light, about 300,000 kilometers per second, fast enough to circle the Earth 7 times in 1 second. Those numbers are impressive, and anything impressive can feel intimidating. But there's something deeper happening inside the human mind. We evolved in small groups. For most of human history, the largest structures we encountered were mountains, forests, and perhaps large animals. Our instincts are tuned to physical threats we can see: storms, predators, fire. When we encounter something vast and complex that we don't fully understand, our brain sometimes treats it like a potential predator. Big plus unknown equals caution. That reaction isn't foolish. It's protective. But sometimes, the scale of modern engineering surpasses our instincts. The Large Hadron Collider is large by human standards, but by cosmic standards, it is tiny. The Earth itself is about 12,700 kilometers across. That's like stacking nearly 500 LHC rings side by side just to match Earth's diameter. And the Earth is small compared to the Sun. You could fit about 1.3 million Earths inside the Sun. And the Sun is just one average star among hundreds of billions in our galaxy. When we zoom out, the collider shrinks into perspective. It's a small ring on a small planet orbiting a medium-sized star in a typical galaxy. That perspective doesn't diminish its engineering achievement. It simply reminds us that reality itself is vast and resilient. There is also something about underground facilities that triggers imagination. Hidden things feel secretive, even if they are publicly documented and toured. The fact that they are out of everyday sight gives them an aura. Imagine if the LHC were built above ground, visible like a highway loop, with transparent walls showing beams circulating inside. It might feel less mysterious, but because it's buried about 100 meters underground, about as deep as stacking 30 apartment floors, and then digging that far down, it feels concealed, and the mind associates concealment with secrecy. Yet the underground location has practical reasons. It shields the machine from surface vibrations. It provides stable temperatures. It protects surrounding areas. Engineering decisions can easily take on symbolic meaning when seen from the outside. There's also the emotional weight of the phrase, most powerful machine. Power suggests potential harm. But in physics, power is about precision and energy scale, not destruction. A microscope can be described as powerful because it reveals tiny details. The LHC is a kind of microscope, not one that uses glass lenses, but one that uses high-energy collisions to reveal smaller structures. It doesn't smash for the sake of smashing. It collides particles to see what they are made of. When we shift the image from giant machine tearing at reality to extremely advanced microscope, the feeling changes. One image suggests aggression. The other suggests curiosity. And curiosity has always driven human progress. The same instinct that once pushed humans to climb mountains and cross oceans now pushes scientists to explore smaller and smaller scales. That instinct can feel risky, but it is also what led to medicine, communication, satellites, and the understanding of gravity and electricity. So perhaps the unease around CERN is not really about physics. It is about scale, visibility, and the speed of modern progress. Technology has grown faster than our instincts can comfortably track, but when we slow down and examine the details, the energy comparisons, the cosmic ray evidence, the safety studies, the machine becomes less like a monster and more like a tool, a very large tool, built carefully, operated cautiously, and designed not to break reality, but to understand it. And sometimes, understanding removes fear more effectively than reassurance alone. There is another quiet force shaping the story around CERN. It isn't physics. It isn't engineering. It's something happening inside the human mind. We are pattern-seeking creatures. From the earliest days of our species, survival depended on noticing connections. A rustle in the grass might mean a predator. Dark clouds might mean rain. A certain plant shape might mean food. The brain became very good at linking events together. Sometimes too good. There's a word for this tendency: apophenia. It means seeing meaningful connections between things that are not actually related. For example, if you look up at the night sky, you see stars scattered randomly, but humans have drawn constellations between them for thousands of years. We see hunters, bears, scorpions, shapes outlined in points of light that are often hundreds of light years apart from one another. The shapes feel real, but they are patterns our minds impose. Now bring that tendency into the modern world. The Large Hadron Collider restarts after maintenance. Around the same time, someone notices a strange news headline, or a logo seems different, or a world event feels unusual. The brain connects the two. CERN turned on, and then this happened. The connection feels meaningful, but is it causal, or is it coincidence? Coincidences are more common than we like to admit. In a world with billions of people and constant global events, something unusual is happening somewhere almost every day. If you look at a calendar and pick a date, you can likely find a surprising event tied to it. But our minds prefer narrative over randomness. Randomness feels uncomfortable. Narrative feels controlled. So when something complex like CERN operates quietly in the background, it becomes a convenient anchor for unrelated events. Another example of pattern seeking is symbolism. People notice the statue of Shiva at CERN, a dancing figure often associated in Hindu tradition with both creation and destruction. That image feels symbolic, so the mind asks, why would a particle physics laboratory display a statue linked to destruction? The answer is cultural and artistic. Shiva's dance represents cycles: creation, preservation, and transformation. It's a symbol of cosmic motion, fitting for a place studying the building blocks of the universe. But symbolism can easily be interpreted as hidden meaning. The mind fills in the story. There's also something called confirmation bias. Once someone begins to suspect that CERN is altering reality, they start noticing details that seem to support that belief. A strange weather event, an unusual news story, a personal memory glitch. Each becomes evidence. Meanwhile, countless normal events pass unnoticed. It's similar to buying a new car and suddenly seeing that same model everywhere. The car didn't suddenly multiply. Your attention simply tuned in. Attention shapes perception. And in the age of the internet, attention spreads quickly. One person posts a theory. Others who already feel uncertain about the world see it. It resonates. It spreads. Soon, a pattern feels solid because many people share it. But shared belief does not automatically equal shared cause. There's also the emotional context of our time. The modern world changes rapidly. Technology evolves. Social structures shift. News cycles move quickly. When the world feels unstable, the mind looks for anchors, explanations. A massive machine studying invisible particles can become a symbol of that instability. It becomes a focal point for diffuse unease. But let's gently ask, if CERN were altering reality, would the effects be subtle memory shifts and odd coincidences? Or would the consequences be fundamental? Physics operates through consistent laws. If those laws changed even slightly, we would not simply misremember brand names. Chemical reactions might behave differently. The sky itself might look unfamiliar. Reality at the deepest level is not delicate in a psychological sense. It is governed by constants measured to astonishing precision. The fine structure constant, a number that describes the strength of electromagnetic interactions, has been measured in distant galaxies, billions of light years away. The value appears the same there as it is here. That consistency suggests stability across immense distances and times. So when we see patterns connecting CERN to unrelated events, it's helpful to pause. The human brain evolved to over-detect patterns rather than under-detect them. In a prehistoric environment, mistaking wind for a predator was safer than missing a real threat. Today, that same tendency can lead us to connect unrelated dots. It's not a flaw, it's a feature of how we think, but awareness of it brings calm. Instead of asking, what if this event happened because of CERN, we can ask, what evidence supports that link beyond timing? Often, the connection rests on proximity, not causation. Two events happening around the same time do not automatically share a cause. The sunrise does not cause the rooster to crow, even if the rooster crows at dawn every day. Correlation is not causation. And understanding that difference helps steady the mind. The story of CERN shows how powerful our pattern-making instincts are. We take scale, mystery, symbolism, and timing, and weave them into narratives. But when we slow down, when we separate physics from perception, the patterns loosen. The collider continues its quiet work. Particles collide, data is recorded, and the broader world unfolds according to countless independent factors. The mind's ability to create meaning is beautiful. It allows art, language, and science itself. But sometimes, stepping back from imagined connections reveals something comforting. Reality is not secretly shifting. It is stable enough that we can measure it with incredible precision, and that stability has endured through forces far greater than any machine humanity has built. Understanding our own pattern-seeking nature doesn't remove wonder, it simply grounds it. And grounding brings peace. Even after understanding the physics, the psychology, and the safety studies, one question still lingers. Why does the idea of CERN opening a portal feel so compelling? Why does they tore a hole in reality travel faster online than particle scattering matches theoretical prediction? Part of the answer is simple. Stories are powerful. A cosmic conspiracy has drama. It has tension. It has hidden forces and secret knowledge. It places humanity at the edge of something enormous and dangerous. Scientists accidentally opened a gateway. Feels like the beginning of a movie. Scientists refined measurements of the Higgs field. Feels like homework. The human brain is wired for narrative. For most of our history, information was passed through stories told around fires. Stories helped us remember lessons, dangers, and values. So when something complex and technical appears, like a 27-kilometer particle accelerator buried underground, the mind naturally wraps it in narrative, and the more mysterious the machine sounds, the easier it becomes to imagine a hidden plot. There is also something emotionally satisfying about the idea that major world events have a single dramatic cause. The world today can feel chaotic. News shifts quickly. Social systems change. Technology moves at a pace that feels hard to track. In that environment, a simple explanation feels comforting. If something strange is happening, there must be a central cause. CERN becomes that cause. It becomes a symbol, not just of physics, but of modern power, global collaboration, and invisible forces shaping reality. The idea that a hidden experiment is altering timelines or opening cracks in space-time gives structure to uncertainty. It turns random complexity into intentional design. But here's a gentle question. Which is more unsettling? The idea that a secret machine is altering reality, or the idea that reality is vast, complex, and not centered around human actions at all? Sometimes conspiracy feels empowering. It suggests someone is in control, even if that control is dangerous. But the universe, as physics describes it, does not revolve around human institutions. Galaxies collide billions of light years away without regard for our experiments. Black holes merge with energies that dwarf anything we can produce. Stars explode with brightness that outshines entire galaxies for weeks. And through all of that, space-time remains intact. The scale difference is staggering. The energy released in a single supernova, when a massive star collapses and explodes, is more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. That's like compressing billions of years of solar output into a brief cosmic flash. Compared to that, the LHC is gentle, yet the mind gravitates towards the human-made machine as the center of drama. Why? Because it's closer, because it's tangible, because it carries the weight of human intention. There's also a certain thrill in believing you've uncovered hidden truth. To say, they don't want you to know this, creates a feeling of insight, of being part of something exclusive. Scientific research, by contrast, is slow and transparent. It involves error bars, statistical significance, and peer review. It doesn't feel secretive, it feels procedural. But procedure doesn't spark adrenaline. Cosmic conspiracy does. Still, if we gently step back, we can see that the quieter story is more remarkable. Thousands of scientists from different nations collaborating peacefully, building a machine that stretches 27 kilometers underground, cooling magnets to temperatures colder than deep space, accelerating particles to nearly the speed of light, all to answer questions about what matter is made of. That story doesn't involve portals, but it does involve curiosity, cooperation, and the desire to understand existence itself. And that might be even more profound. There's also something about the phrase, tearing reality, that resonates emotionally. Reality feels like something solid, dependable. To imagine it tearing suggests fragility. But as we've seen, reality, in the language of physics, is made of stable fields and consistent laws. Those laws have survived for about 13.8 billion years. They've endured cosmic events beyond imagination. If reality were as fragile as rumor suggests, it would not have lasted this long. Sometimes, the more exciting explanation feels more meaningful, but excitement does not equal truth. And the quieter truth, that the universe is stable enough to be studied carefully, carries its own kind of wonder. It tells us that existence is not balanced on a knife's edge. It is structured, reliable, mathematically elegant, and that stability allows life, thought, and curiosity to emerge. So perhaps the appeal of cosmic conspiracy is not about physics at all. It's about story, about the human need for meaning in a vast universe. But meaning doesn't require danger. The act of exploring the building blocks of matter is already extraordinary. No portal needed, no hidden agenda, just the quiet hum of a machine beneath the earth and the steady unfolding of understanding. And sometimes the real mystery is not whether reality can be torn, it's how something so vast and ancient can be stable enough for us to ask the question at all. Let's return gently to the Mandela effect, not as a sign of torn timelines, but as a window into how the mind works. Because when people say, "I clearly remember it being different," they are not lying. The memory feels real. It feels vivid. Sometimes it feels certain. So what is happening? Memory is not like a hard drive storing perfect recordings. It is more like a living reconstruction. Each time you remember something, your brain rebuilds it from pieces, bits of sensory detail, emotion, context, and expectation. It stitches those pieces together into a coherent story. That reconstruction usually feels seamless, but it is not exact. Think about a childhood memory, perhaps a birthday party, a room filled with people, a cake with candles. If you and a sibling compare memories of that same day, you may notice differences: the color of the balloons, who stood where, what song played. Neither of you is inventing the memory, but each of you is reconstructing it through your own perspective. Now multiply that by millions of people recalling a logo, a brand name, or a movie line. If a phrase sounds more natural in one form, the brain may quietly adjust it to fit language patterns. For example, a movie quote might feel smoother with slightly different wording. Over time, people repeat the smoother version. It spreads. It feels correct. Then, when someone checks the original line and finds it different, it feels like reality shifted. But what shifted was collective memory. There are experiments that show how easily memory can be influenced. In some studies, participants watched short videos of car accidents. Later, researchers asked them questions. When the question used stronger words like smashed instead of hit, participants were more likely to remember broken glass. Even when no broken glass was present in the video, a single word shaped memory. That's how flexible it can be. Memory prioritizes meaning and coherence over perfect accuracy. This flexibility is not a flaw. It helps us adapt. It helps us form narratives. It helps us learn from experiences without storing every tiny detail. But it also means that certainty does not guarantee accuracy. Now connect this to CERN. When people already feel uneasy about large scientific experiments, and then they notice a memory discrepancy, it's easy to link the two. Something feels off, and CERN restarted recently. The brain searches for cause. But here's a calming perspective. Memory shifts have been documented long before the Large Hadron Collider existed. People have always misremembered details collectively. Shared false memories are not new. What is new is the internet. In the past, if someone misremembered a logo, they might never discover that others shared the same false memory. Today, someone posts, "Does anyone remember it this way?" Thousands respond. The shared memory feels validated. It becomes a phenomenon. The internet amplifies coincidence into pattern, and pattern into narrative. Another gentle thought: if reality itself had shifted, if timelines had diverged, would the changes be limited to brand names and movie quotes? Or would deeper structures change? Physical constants determine the behavior of atoms. Atoms determine chemistry. Chemistry determines biology. Even tiny shifts in fundamental constants could prevent stars from forming. The strength of gravity, the charge of the electron. These values are measured with astonishing precision. They appear consistent across galaxies billions of light years away. If the vacuum state of the universe had shifted, or if we had moved into a neighboring universe with slightly different physics, the consequences would not be subtle. They would be cosmic. But what people notice are small cultural differences. Spelling variations, logo designs, lyrics. That suggests a psychological source rather than a physical one. And there is something comforting in that realization. The Mandela effect is not evidence of a fractured universe. It is evidence of how human memory works. And that in itself is fascinating. Your brain holds billions of neurons, tiny cells connected in networks more complex than any machine we've built. Those networks reconstruct experiences constantly. They are dynamic, adaptive, creative. In some ways, the brain is more mysterious than the collider, because while we can measure particle collisions with incredible precision, the inner workings of memory are still being explored. So instead of seeing memory shifts as cracks in reality, we can see them as reminders, Reality is stable enough that we can compare notes, stable enough that discrepancies stand out, stable enough that we can study memory scientifically. The Large Hadron Collider operates in the world of quarks and bosons. The Mandela effect operates in the world of neurons and cognition. They are separate realms. One does not alter the other, and understanding that separation brings calm. It reminds us that not every unsettling feeling points to a cosmic cause. Sometimes it points inward, to the beautiful, complex way our minds construct the world. And that construction, though imperfect, is part of what allows us to ask these questions in the first place. There is one more layer to the story that often fuels imagination: imagery, symbols, visual details that feel loaded with meaning. If you search for pictures of CERN, you'll likely see the long underground tunnel, lined with cables and magnets, stretching into the distance like a metallic corridor. It looks almost futuristic, almost cinematic. And then there is the statue. Outside stands a statue of Shiva, the dancing figure from Hindu tradition. Shiva is often associated with cycles of creation and destruction. In artistic representations, Shiva dances within a ring of fire, symbolizing the rhythm of the universe. For some people, that image feels deeply symbolic: a particle collider studying the birth of matter, a statue representing cosmic cycles. The mind connects them, and then a question forms: is there hidden meaning here? But let's slow down gently. The statue of Shiva was a gift from India to CERN. It represents the cultural connection between science and the broader human search for understanding. Shiva's dance is often interpreted as the dance of particles: constant motion, transformation, balance between creation and dissolution. It's poetic. It's artistic. It is not a ritual object. Symbols have always accompanied science. Look at old observatories built like temples. Look at early space missions named after mythological figures: Apollo, Artemis. These names and symbols do not imply supernatural intention. They reflect the human tendency to connect new discoveries with older stories. When something as abstract as quantum physics is being studied, symbolism helps people relate. But symbolism can also be misread. A ring-shaped machine underground can feel like a ritual circle in certain stories. Magnets colder than outer space can sound eerie when described without context. Dark tunnels, lit by artificial light, can resemble scenes from science fiction films. The visual language of advanced technology often overlaps with cinematic imagination. That overlap fuels speculation, but visual similarity does not imply hidden purpose. Another example is the idea that the LHC recreates the Big Bang. That phrase is often used in headlines, and when paired with dramatic images, it can sound apocalyptic. But what scientists mean is much more precise. They recreate extremely high temperatures in a tiny region for a tiny fraction of a second, similar to conditions just after the Big Bang, not the cosmic explosion itself. It's like heating a drop of water to the temperature of the sun for a brief instant. Inside a controlled lab, you have not recreated the sun. You have recreated a property of it: temperature. At small scale, the language can sound larger than the reality. And when dramatic language meets dramatic imagery, the imagination expands. It's also worth noticing how certain words carry emotional weight: collider, smashing, dark matter, God particle. The Higgs boson was nicknamed the God particle in popular media, not because physicists believe it is divine, but because the nickname made for a compelling book title. Yet that name stuck, and for some people, it added mystique. The actual role of the Higgs boson is technical. It relates to how particles acquire mass through interaction with the Higgs field. That's less dramatic than God particle, but more accurate. When we step back, we see how layers build. Large underground ring, statue of a cosmic dancer, particles called strange, fields called dark. The mind weaves them into a story. But beneath the story lies ordinary human activity. Engineers tightening bolts, physicists analyzing graphs, technicians monitoring cooling systems, people eating lunch in a cafeteria and discussing data. The everyday reality of CERN is far less mystical than its imagery suggests. And perhaps that contrast is important. The universe itself is already filled with genuine wonder. Galaxies stretching millions of light years across. Distances so vast that light traveling at 300,000 kilometers per second takes millions of years to cross them. Stars collapsing into neutron spheres the size of a city, but with mass greater than the sun. Quantum particles flickering in and out of existence in empty space. None of that requires secret symbolism. It exists regardless of statues or headlines. Symbols help us frame understanding, but they do not drive physics. The statue of Shiva does not influence particle collisions. The name God particle does not alter mass generation. Imagery can inspire curiosity. It can spark imagination, but it can also mislead when taken too literally. So when we see powerful symbols attached to advanced science, it helps to separate art from mechanism. Art speaks in metaphor. Science speaks in measurement. CERN operates in measurement. Magnetic fields guide beams. Sensors record traces. Computers analyze patterns. No rituals, no hidden gates. Just the steady hum of technology doing what it was designed to do. And sometimes, understanding that simplicity dissolves the drama, the statue becomes art, the tunnel becomes infrastructure, the language becomes precise, and reality remains what it has always been: vast, stable, and waiting to be explored. Not through symbols, but through careful observation. By now, we've gently examined black holes, wormholes, vacuum decay, extra dimensions, memory shifts, symbolism, and the psychology of fear. But let's pause and return to the core phrase: tear a hole in reality. It sounds dramatic, but what would that actually mean in physical terms? Reality, as physics describes it, is made of quantum fields and space-time. Fields that stretch across the universe. Space-time that bends around mass and energy. So to tear reality would mean disrupting those fields or ripping space-time itself. Let's think about space-time first. Space-time can bend. We know this because gravity bends it. The Earth bends space-time enough to hold the Moon in orbit. The Sun bends it enough to hold planets. Black holes bend space-time so strongly that not even light escapes. But bending is not tearing. When two black holes collide, each heavier than dozens of suns, they release gravitational waves. These waves ripple through space-time like ripples across a lake. When scientists detected gravitational waves for the first time, the distortion they measured was unbelievably small, smaller than the width of a proton. Even events involving massive black holes merging billions of light years away do not tear space-time apart. They stretch it slightly, then it settles. So if cosmic events involving masses far beyond anything we can produce do not tear space-time, what would it take to rip it? The energy required would be enormous, far beyond human capability. To get a sense of scale, consider the energy released by the sun every second. In 1 second, the sun produces about 4 times 10 to the power of 26 joules of energy. That's enough to power human civilization for hundreds of thousands of years. The LHC's total beam energy is measured in megajoules. Millions of joules. That sounds large until you compare it. Millions versus 10 to the power of 26. It's like comparing a cup of water to an ocean. And even the sun's energy does not tear space-time. It simply bends it gently. Now think about quantum fields. To tear reality at the field level would mean disrupting the fundamental structure that defines particles and forces. But fields are not thin sheets stretched tight. They are stable frameworks, described by equations that have held true across billions of light years of space. When particles collide in the LHC, they create excitations, tiny ripples, In these fields, those ripples are localized. They fade almost instantly. It's like tapping the surface of a pond with your finger. You create small waves, but the pond remains. To truly disrupt a field everywhere, you would need to alter its lowest energy state globally, something like vacuum decay. And as we've discussed, if that were possible at collider energies, cosmic rays would have triggered it long ago. Another way to approach the question is this: if reality could be torn locally, what would that look like? Would there be a visible crack in the air? Would space fold like fabric? In physics, space is not a material that can split open like cloth. It is a geometric structure. You can curve geometry, you can stretch it. But tearing implies separating it into pieces. There is no known mechanism in established physics that allows for space-time to rip open and expose something behind it. Even inside black holes, where space-time curvature becomes extreme, we describe singularities mathematically, points where our equations break down. But those singularities are not tears in the fabric exposing another realm. They are limits of our current understanding. And importantly, they occur under conditions involving masses far greater than anything humanity can gather. So perhaps the phrase tear reality comes more from metaphor than mechanism. It expresses fear that something foundational might break. But the foundations of physics are not fragile in that way. They are consistent. The speed of light remains the same in every experiment. The charge of the electron remains constant. The gravitational constant does not fluctuate with collider schedules. Measurements made decades ago still match measurements made today. Reality has an astonishing stability. The same equations describing hydrogen atoms on Earth also describe hydrogen in distant galaxies billions of light years away. That kind of consistency suggests resilience. So when we ask what it would mean to tear reality, we begin to see how enormous that task would be. It would require energies and conditions comparable to those at the birth of the universe itself. Not localized sparks, but global transformations. And even the birth of the universe was not a tear. It was an expansion. Space-time did not rip apart. It expanded from an incredibly hot, dense state into the vast cosmos we observe. Perhaps the deeper fear is not about physics. Perhaps it's about control. The idea that humans might accidentally push beyond a boundary we do not fully understand. But the boundaries of physics are not crossed casually. They are approached slowly, tested carefully, and compared against nature itself. And nature remains the ultimate experimenter. If reality were easy to tear, the universe would show scars. But when we look out into the night sky, we see continuity. Light from distant stars arrives after traveling millions or billions of years. It arrives intact, carrying information about galaxies long gone. That continuity is powerful evidence of stability. So maybe the better question is not whether reality can be torn, but how it has remained so steady, so reliable, across scales so vast and times so long. That stability is not something a 27-kilometer ring underground can unravel. It is something that allows that ring to exist in the first place. And that thought shifts the tone from fear to wonder. Because the real mystery is not fragility, it is endurance. Let's imagine, just for a moment, that reality could be broken, not in a dramatic movie way, but in a subtle way. If something fundamental shifted, a constant changed, a field altered, would we notice? Or would everything simply adjust, leaving us unaware? It's a quiet, interesting question. Physics depends on constants, numbers that seem woven into the structure of the universe. For example, the speed of light, about 300,000 kilometers per second. That's fast enough to circle the Earth 7 times in 1 second. That number appears to be the same everywhere we measure it. Another constant describes the strength of electromagnetism, the force that allows atoms to hold together. If that number were slightly larger, electrons might cling too tightly to nuclei, chemistry would change. If slightly smaller, atoms might not hold together at all. Even small shifts could have enormous consequences. To picture how sensitive this is, imagine a piano string tuned just right. If you tighten it too much, it snaps. If you loosen it too much, the note goes flat. The balance matters. The universe appears tuned in a way that allows stars to shine steadily for billions of years. Our sun has been burning for about 4.6 billion years already, long enough for life to evolve on Earth. If the strong nuclear force were even a few percent weaker, stars might not form stable elements beyond hydrogen. If gravity were slightly stronger, stars might burn too quickly and collapse early. These balances are delicate, but delicate does not mean unstable. It means precise. So if something fundamental shifted even slightly, we would likely notice in dramatic ways. Atoms might not behave the same. Chemical reactions might change. The sky itself might look different. But here's the reassuring part. We observe light from galaxies billions of light years away. That means the light left those galaxies billions of years ago, long before Earth formed. And when we analyze that light, we see the same atomic fingerprints we see here. Hydrogen behaves the same way. Oxygen behaves the same way. The constants appear consistent across enormous distances and times. That tells us something powerful. Reality has not been quietly drifting or fracturing. It has been remarkably stable. Another thought experiment helps. If the Large Hadron Collider could somehow break reality locally, would that change remain confined? Physics suggests that fundamental fields are not isolated patches. They extend everywhere. A true shift in the vacuum state, if it were possible, would spread at the speed of light. That means once it began, it would not remain hidden underground. It would propagate outward rapidly. But we do not observe any expanding bubbles of altered physics, no sudden changes in star behavior, no unexplained shifts in atomic structure. Instead, experiments across the world, in different laboratories, in different countries, continue to measure the same values. The laws remain steady. There's also something subtle about how we experience reality. We often assume we would notice if something changed. But notice what? If all of physics changed simultaneously, every atom, every photon, there would be no before and after reference point within the new system. Yet the fact that we can compare past measurements to current ones and find consistency suggests continuity. For example, atomic clocks measure time with astonishing precision, losing or gaining less than a second over millions of years. If fundamental constants shifted, atomic clocks around the world would drift unpredictably, but they remain in agreement. Another calming point: quantum field stability has been studied deeply. The Higgs field, for example, gives particles mass. Its value appears uniform across space. The discovery of the Higgs boson in 2012 confirmed aspects of this field's behavior. If the Higgs field suddenly changed, particle masses would change. The mass of the electron, crucial for chemistry, would shift, but chemistry behaves consistently. Water still freezes at 0 degrees Celsius under normal pressure. Stars still produce light through nuclear fusion in predictable ways. These observations suggest that reality is not wobbling at its edges. It is stable. There is a philosophical angle here too. Sometimes the fear that reality might break reflects a deeper uncertainty. The modern world changes quickly. Technology shifts rapidly. Cultural norms evolve. When society feels unstable, it can project that instability onto the cosmos. But the cosmos operates on timescales far beyond human headlines. Galaxies rotate over hundreds of millions of years. Light travels for billions of years before reaching us. Compared to that, human events are brief. And through those vast stretches of time, the same physical laws have governed everything we observe. So if reality could be broken, yes, we would likely notice. Not through small memory quirks, not through brand name variations, but through profound physical changes. And we do not see those. Instead, we see continuity. We see stable atomic spectra in distant galaxies. We see consistent gravitational behavior in planetary orbits. We see the same speed of light in every experiment. That consistency is not fragile, it is resilient. And perhaps the most reassuring thought is this: if reality were as easy to break as rumor suggests, it would not have survived the violent early universe. It would not have survived supernovae, black hole mergers, or cosmic radiation. Yet here it is, steady enough for life to form, stable enough for consciousness to arise, stable enough for us to build machines that study it. If reality could be broken casually, we would not be here to wonder about it. And that realization brings a quiet sense of grounding, because the universe, vast and strange as it is, appears far stronger than our fears. After exploring fears, symbols, psychology and energy scales, something interesting becomes clear. We don't need portals or torn timelines for reality to be astonishing. The universe is already strange beyond everyday imagination. Take quantum entanglement. Two particles can become linked in such a way that measuring one instantly affects the description of the other, even if they are separated by great distances. Not because information travels faster than light, it doesn't, but because at a deep level, their properties are described together. That idea alone feels almost magical. Imagine flipping two coins in different cities, and somehow knowing that if one lands heads, the other will land tails, not because of a signal sent between them, but because they were prepared in a linked state. It challenges intuition, yet it has been tested in experiments again and again. No portal required, no cosmic accident, just the quiet strangeness of quantum fields. Then there is space-time curvature. Mass bends space-time. The Earth bends it enough to keep the Moon in orbit. The Sun bends it enough to guide planets. Black holes bend it so intensely that time itself slows dramatically near them. If you could hover near the edge of a black hole, safely in theory, time for you would pass more slowly compared to someone far away. Hours for you might correspond to years elsewhere. That's not science fiction. That's a prediction, confirmed by precise measurements of gravity and time dilation near Earth. Even our GPS satellites must account for tiny time differences caused by both speed and gravity. Without those corrections, your phone's map would drift by kilometers each day. Reality already bends and stretches in ways that feel extraordinary. And then there are vacuum fluctuations. Empty space is not truly empty. Even in perfect vacuum, tiny particle-antiparticle pairs appear and disappear constantly. These fluctuations are measurable. The Casimir effect, where two metal plates placed very close together experience a tiny force due to vacuum fluctuations, has been observed in laboratories. That means the nothingness between objects is not nothing at all. It is alive with subtle activity. And consider the scale of the cosmos. The Milky Way galaxy is about 100,000 light-years across. Light travels at 300,000 kilometers per second. Even at that speed, it takes 100,000 years to cross our galaxy. To picture that, imagine turning on a flashlight at one end. The beam would take longer than all recorded human history to reach the other side. And our galaxy is just one among perhaps hundreds of billions in the observable universe. Distances so vast that numbers lose emotional meaning. Yet the same physical laws operate across those distances. The same electron mass, the same gravitational constant, the same quantum behavior. No cracks in the sky, no shifting constants after collider restarts. Just continuity. Even the origin of the universe is deeply mysterious. About 13.8 billion years ago, space-time was extremely hot and dense. It expanded rapidly, not exploding into space, but space itself expanding. That distinction matters. The Big Bang was not a bomb in pre-existing emptiness. It was the rapid stretching of space-time, and even that event, unimaginably energetic, did not tear reality. It defined the beginning of its expansion. When physicists study particle collisions, they are not trying to recreate that event in full. They are recreating tiny aspects of its conditions, temperature, density, for brief moments in tiny regions. It's like creating a small flame that shares the temperature of the sun's core without recreating the sun. The real mystery is not fragility, it's coherence. How does a universe filled with quantum uncertainty produce stable atoms? How do simple particles combine into molecules, cells, minds? How does a cosmos governed by abstract equations give rise to consciousness capable of asking questions about itself? That is far more profound than the idea of a torn dimension. And the Large Hadron Collider plays a role in this exploration. It helped confirm the Higgs boson, a particle linked to the Higgs field, which gives mass to fundamental particles. Without mass, matter would not clump together, stars would not form, planets would not coalesce, life would not emerge. Understanding the Higgs field deepens our knowledge of why existence has structure. And yet, even with that discovery, many questions remain. Dark matter still puzzles us. Dark energy, the mysterious force accelerating cosmic expansion, remains even more enigmatic. We observe galaxies moving apart faster and faster. Something is pushing space-time outward. That force dominates the universe's energy budget, about 68% of it, yet we barely understand it. The universe is not fully explained. It is unfolding, and perhaps that is the most humbling thought. CERN is not breaking reality, it is gently probing it. Reality is not thin glass waiting to shatter. It is a vast, resilient structure that has survived cosmic violence far beyond our engineering. The true wonder is not that we might tear a hole in existence, it's that existence is stable enough for us to study it all, stable enough for stars to burn steadily, stable enough for life to evolve slowly, stable enough for curiosity to arise. The universe does not need added drama. Its genuine features, entanglement, curvature, vacuum energy, cosmic expansion, are already extraordinary. No hidden portal required, just a quiet hum underground, and the steady expansion of understanding. And perhaps, in that quiet pursuit, there is something more profound than any conspiracy. A species on a small planet, asking careful questions about the structure of reality itself. We began with a question that felt dramatic. Could CERN really tear a hole in reality? The phrase itself carries weight. It suggests something fragile, something stretched thin, something that might split open if pushed too far. But as we've slowly explored the physics, the scale, the psychology, and the symbolism, a different picture has emerged. Reality is not thin fabric. It is not glass under pressure. It is a vast, stable structure shaped by fields and forces that have endured for about 13.8 billion years. For billions of years before humans ever built machines, the universe conducted experiments far more powerful than anything we can create. Cosmic rays, particles from distant explosions, strike Earth with energies higher than those in the Large Hadron Collider. Stars explode in supernovae, releasing in seconds more energy than our Sun will produce in its entire 10 billion year lifetime. Black holes collide, sending ripples through space-time that travel across galaxies. And through all of it, the laws remain steady. The speed of light does not flicker. The charge of the electron does not drift. The structure of atoms does not collapse. Reality holds. The Large Hadron Collider, impressive as it is small by cosmic standards. Its 27-kilometer ring, long enough to drive across a city, is tiny compared to the 700-kilometer diameter of Earth, tiny compared to the 1.3 million Earths that could fit inside the Sun. tiny compared to galaxies that stretch 100,000 light-years across, distances so vast that light itself takes 100,000 years to cross them. The collider does not rival the universe. It studies it. It accelerates protons, particles smaller than atoms, and allows them to collide in carefully monitored conditions. The energy involved in each collision is concentrated but modest overall, comparable to the energy of a flying mosquito, focused into something unimaginably small. That concentration allows us to glimpse deeper layers of matter. It does not grant us the power to rewrite space-time, and yet, the fear around CERN tells us something important. It tells us that reality matters to us. It tells us that the stability of existence feels precious. It tells us that we are aware, at some level, of how extraordinary it is that the universe works at all. Perhaps the deeper unease isn't about machines. Perhaps it's about standing at the edge of knowledge. When humans first looked up at the night sky, they did not understand stars. When we first learned that Earth orbits the sun, it felt destabilizing. When we discovered that atoms are mostly empty space, it challenged intuition. Each step deeper into understanding has felt unsettling at first, but each step has also revealed deeper structure. The discovery of the Higgs boson did not tear reality. It confirmed part of the mechanism that gives particles mass. The study of quantum fields did not unravel space-time. It revealed that what feels solid is woven from vibrations in invisible fields. The exploration of dark matter has not unleashed danger. It has highlighted how much of the universe remains unknown. CERN is not attempting to rip open the universe. It is attempting to listen more carefully, to measure more precisely, to test ideas that have been built over decades of careful thought. Thousands of scientists from around the world collaborate there, not in secrecy, but openly, publishing data, checking one another's work, debating interpretations. It is a human effort driven by curiosity, and curiosity is not the same as recklessness. If reality were easy to tear, it would not have survived the early universe, a time far hotter and denser than anything we can recreate. If reality were brittle, it would not have endured billions of years of cosmic radiation. If the vacuum were unstable at collider energies, natural cosmic rays would have triggered collapse long ago. But the sky above us remains unchanged. Stars continue to shine, atoms continue to bind, time continues to move forward at the same steady pace. And perhaps that is the quiet conclusion. CERN is not tearing a hole in reality, but it is doing something that can feel almost as profound. It is gently pulling back layers of understanding. It is revealing that beneath the surface of everyday experience lies a universe more intricate than we imagined. Fields that vibrate, space-time that curves, particles that flicker in and out of existence. None of it fragile in the way fear suggests, all of it stable enough to study, stable enough to sustain life, stable enough to allow consciousness to ask questions about itself. And maybe that is the real wonder. Not that we might break reality, but that reality is deep enough to explore, resilient enough to endure, and mysterious enough that even after building a machine 27 kilometers long, colder than outer space, guiding particles at nearly the speed of light, we still stand at the beginning of understanding. The universe does not tremble beneath our curiosity. It invites it, and that invitation is far more powerful than any rumor of a torn dimension. In the end, the quiet hum beneath the earth is not the sound of reality unraveling. It is the sound of humanity listening closely. And reality, vast and steady, continues to hold.